Hey guys, hope you're all well. Here we have chemistry from November 2024. If you want to download the paper, check the description below. Which one of the following compounds has hydrogen bonds between its molecules? Okay, so I would always just go quickly and draw this all out. So there's a CH3. I'm not going to draw all the hydrogens. Then it's got a CH2, which is a C with two hydrogens. And then we've got a C with an H. And then we've got an oxygen. So that oxygen would obviously have to be a double bond so that this carbon has four things surrounding it. Now, I could rather put the double bond oxygen there and then the hydrogen like that. Then we'll realize that this is actually just a plain old aldehyde where the double bond oxygen is on the side. So that is an aldehyde. There's no hydrogen bond there. For a hydrogen bond, you're looking for a molecule that has a hydrogen bonded with either nitrogen, oxygen, or fluorine. Kevin, but there's an oxygen and a hydrogen. Yes, but they're not bonded together, okay? They are each bonded to the carbon, but they're not bonded to each other. Okay, let's look at this one. So that one has a CH3. Then it's got a carbon. Then it's got a oxygen and another oxygen. So that's going to be like an ester. So the one's going to be a double bond. The other one's going to be there. And then it's got a CH3. Okay, so that's just a plain old ester. There's no hydrogen bonded to nitrogen, oxygen, or fluorine. So it's not going to be there. It's probably going to be this one because we can see there's an OH. But let's just double check. CH3. Then there's a CH2. Then there's a CH2 again. And then there's an OH. Boom. There we have an oxygen bonded to a hydrogen, and so the answer is C. Which one of the following is a correct general formula for carboxylic acids? Okay, so what I would go and do is I'd go draw a basic, like a 3-carbon carboxylic acid for myself if I was in an exam, if I can't remember its general formula. And then I would try to figure it out. So I see that there's 3 carbons. Okay, so that's C3. Then there's going to be 1, 2, 3, 4, 5, 6 hydrogens. Okay, and then there's always going to be 2 oxygens. So then I would try simplify that using N's and all of that. So if this is N, then this has to be double that. And then there's always 2 oxygens. That's just always going to be, no matter how long or how short the carboxylic acid is, it's always going to have 2 oxygens, okay? Even if you have like a 6-carbon carboxylic acid, 1, 2, 3, 4, 5, 6, it's only the oxygen part at the end that makes it a carboxylic acid, so there would still only be 2. So we're looking for something like that, CnH2nO2, CnH2nO2, there we go. Study the reactions below. So reaction 1, we have a certain molecule reacted with concentrated sulfuric acid, and we form compound P plus water. And then we've got reaction 2, which uses, so it uses compound P, which is from here. They then use hydrogenation to form compound Q. Which of the following combinations is a correct IUPAC name of compounds P and Q? Interesting. Okay, so I'm actually going to start us off over here. We know that hydrogenation is when you add hydrogen to an alkene. Remember that alkenes are keen to do addition reaction, and this is one of them, hydrogenation. I'll give you a little example. If we have an alkene like that, let's go fill in all of its hydrogens. Okay, so there is an alkene. So what happens is that, and if you react that with hydrogen, then what happens is that this little double bond here would break, and then you would form 2 open spots over there, and then this hydrogen, remember it's H with another H, one of them would go there, and one of them would go there. That is hydrogenation. So I then know that this compound P must be an alkene, and I know that this must be an alkane. Because once you add these hydrogens on, then you have an alkane. Okay, so the answer for compound Q, it cannot be these ones. So those are completely out. Okay, so it's definitely going to be one of these. So let's have a look. We're going to quickly go draw this molecule. Okay, so let's draw out that molecule, this one over here. And it would go, so it's got a CH3. So let's do all the hydrogens and everything just so we can get a clear look at it. Then it's got a CH2. Then it's got a CH. And then it's got an oxygen with an OH. Oh, okay, so it's an alcohol like that. And then it's got a CH3. Okay. They then react that with some concentrated H2SO4. Now we know that the product, compound P, is an alkene because it's the same compound P over here. So we know that we're going to produce an alkene. So we know that we need to produce a double bond. So that means we're going to have to lose this OH for sure. Now we're going to have to use Zaitsev's rule to figure out whether we're going to lose the hydrogen from this carbon or whether we're going to lose the hydrogen from this carbon, so that we can either make the double bond there or the double bond there. It's very important. So we're going to use Zaitsev's rule to figure out the major product. Okay. Now remember, we've got that riddle that goes: the richer get richer and the poorer get poorer. And remember, whenever we look at this riddle, we're always talking about hydrogen. Now, we're not going to look at the first part. That is only for addition, and that would be called the Markovnikov. Something like that. Markovnikov. Yeah, you know what I'm talking about. And then the poorer get poorer. That's what we're going to look at now. That's when you're doing elimination. And that is why that's the one we call Zaitsev. So we are going to look at these two hydrogens. So this one here and this one here. Who is the poorest in hydrogen? Well, this one has 2 hydrogens. This one has 3. So the poorest one is the one that has 2. And the riddle tells us that the poorer gets even more poor. So we're going to lose the hydrogen from this carbon over here. Whether you choose the top one or the bottom one doesn't make a difference. I'm going to choose the bottom one, so we're going to lose that. And so when we then get our product, we're going to have the original CH3, which we still have in the beginning, this part over here. Then we're going to have C, and then we've still got this hydrogen up here. But then we've lost this hydrogen that was here, so that's no longer there. And then we've also lost the OH that was originally there. And then we've still got a CH3. Now we're going to have to put a double bond over there just to make sure that the carbons have 4 things surrounding them. So that is what compound P is going to look like. It is a alkene, 4 carbons, so it's BUT. And we can see that the double bond is on carbon 2. So it's going to be the one that's on carbon 2. Many learners are going to say the one on carbon 1, but that is because you are then forgetting about the Zaitsev rule. So the answer is B. The potential energy diagram below is for the following hypothetical chemical reaction where we've got X plus Y going to Z. Which of the following combinations of values for the heat of the reaction and the activation energies can be obtained? Okay, so don't even look at this right now. Let's make sure we understand what's happening. So this part over here is the original energy. So it's the energy at the start of the reaction. Then this part over here, this is the energy at the end of the reaction. Okay, that's if we're going in the forward direction. If you're going in the reverse direction, then obviously this is the energy at the start, and then this is the energy at the end. Okay, now in order for the reaction to actually be able to start when you're going in the forward direction, you got to get the energy from here up to here. So that energy that you need is called the activation energy. Okay? But everything I've said there, that is for the forward reaction. Okay? That is for, so the red is for the forward. If the reaction goes in reverse, then it starts over here. So let's do the green will be in reverse. So then this part over here would be the energy at the start, but that's if we're doing the reverse reaction. And then this over here would be the energy at the end, but that's when we're doing the reverse reaction. And then to get the reaction to actually start, you would have to go all the way from here up to the top over here. So you would have to go all the way, or let's just do a dotted line over here. You would have to go all the way up to there. And so that would be your activation energy in green of the reverse reaction. Okay, so remember, if the reaction diagram goes like this, that's the forward. If you go this way, that's the reverse. So the first thing they talk about is this delta H. Now, delta H is always going to be your energy of your product minus your energy of your reactant. And they've asked us to do it for the forward reaction. So if you look at the energy of the product, which would be here if we're going in the forward direction, then you can see that this energy is at a lower value than this starting energy. So if you had to go work out the delta H for that reaction, would you get a positive or a negative? Well, you would have a smaller value subtracting a larger value. So you'd get a negative delta H. So the answer cannot be C, because that's got a positive delta H. Okay. So we still have quite a lot of options available, don't we? Well, okay, I think the next part's quite easy. If you go in the forward direction, this EA, that's called your activation energy. Now, if you compare the activation energy of the forward compared to the activation energy of the reverse, the forward activation energy is less. So we want the forward to be less. So here it can't be this one because that's 300 and then this is 100. But we said we want the forward activation energy to be less, so it can't be that one. And then likewise, it also can't be B. So it would have to be, the answer would have to be D. Initially, an equal number of moles of hydrogen gas and iodine gas are mixed in a closed container. The reaction reaches equilibrium at a constant temperature according to the balanced equation. Which of the following will always be true at equilibrium? Okay, well, it's definitely going to be A, but let me explain. So we know that if we look at this reaction over here, it's in a 1-to-1 ratio. That's not the reason that these two are the same, by the way. That's the first part, is that these are in a 1-to-1 ratio. Secondly, they gave us an equal number of hydrogen moles and iodine gas moles. So if you, for example, start off with, let's say they gave us 7 moles of hydrogen and 7 moles of iodine, it's even like in a KC table. Check this out. If we've got our initial change, then moles at equilibrium. Okay, I'm not going to go further to the concentration at equilibrium because that's not relevant for this quick little explanation. Then we're going to put our reaction, H2 plus I2 gives you 2HI. So let's say, for example, we started off, as an example, we started off with 7 and 7 and 0. Then, because they are in a 1-to-1 ratio, if this one goes down by X, then this one would also have to go down by X. Because for every 1 mole of this one that reacts, 1 mole of this one also reacts. So let's say the change is minus X. Okay? So then how many moles would you have left over at equilibrium for the hydrogen? Well, it would be 7 minus X. And for the iodine, it would also be 7 minus X. So at equilibrium, they are actually saying concentration over there. My bad. So let's just go one step further. So we know that the volume of the container would be a value of like 2 decimeters, for example. So to work out the concentration of this one, we use the formula C equals to N over V. So that would be 7 minus X over 2, for example. But it would be the exact same for that one because the container volume is the same for all components that are in the reaction. And so their concentrations are going to be exactly the same. This one, it'll be totally different. It would be like the moles of equilibrium would be X, and then its concentration would be X over 2. So it's not the same. But these two are always going to be the same because of 2 reasons. Number one, their mole ratios are exactly the same, 1 to 1. And they were given exactly the same amount at the beginning. If I change any one of those things, it wouldn't work. For example, if I made this an 8, well, then it wouldn't work. Or if their change wasn't the same, maybe this one was minus X, but this one changes by minus Y, then suddenly they can't be the same when you get to the concentration. But because this part is the same for both, and this part would be the same for both, why? Why would this part be the same? Because that has to do with the mole ratios, and we can see that they are the same. Consider the following reaction at equilibrium. Okay, so we've got a reaction, they give us the delta H. Which of the following changes to the reaction will increase the yield of SO3? So they pretty much want you to do something that will cause the forward reaction to be favored. Okay, so if we add more oxygen, think about Le Chatelier. What will the system try and do? So we add more oxygen, therefore, system will try to decrease the amount of oxygen. Remember, the system always does the opposite. So if we add more oxygen, then the system will try to decrease the amount of oxygen. How will it do that? Will it do that by going in the forward direction or in the reverse? Well, it will do that by going in the forward, because if you go in the forward, then the oxygen becomes less because it's a reactant. And that is what we want. We want the SO3 we want the forward reaction to be favored so that we can increase the amount of SO3. So the answer is A. The table below shows the ionization constant. Okay, so what is the ionization constant? I don't want you to panic when you see this. The Ka number, all it is the following. It's a number that tells you how strong an acid is. Okay, the higher the number, stronger the acid. Okay, and when something is a strong acid, so when something is a strong acid, then it means it loves to ionize. That means that when you put a strong acid in water, for example, it will react with that water like crazy, and it will give away its hydrogens or its protons, and it will cause lots of H3O pluses to be produced. For example, HCl is a strong acid, so when you put it in water, it loves to ionize. So what that means is that think about the word ionize. We're going to produce some ions, and so the hydrogen gets given to the H2O, so you end up producing a Cl minus with a H3O plus. So because HCl is a strong acid, you will produce a lot of this because it really wants to react with the water. Whereas if something is a weak acid, it doesn't really want to. Okay, so consider the following statements. Right, now if you look at the Ka value, that is a really small number. To the -5, that means it's like 0,0000 something, like, for example, 15. Let me actually give you the exact value. So if you have, let me write it here. If you have 1.5 times 10 to the minus 5, that means that the comma or the decimal is actually 5 places to the left. So it's going to be So you're going to go 1, 2, 3, 4, 5, and you're going to put it there. So you're going to end up with 0,0000015. So these are very small numbers. So Ka is a number that tells you how strong an acid is. The higher the number, the stronger the acid. So because these numbers are low, they are weak. So are they both weak? Hell yeah. Then butanoic acid is stronger than ethanoic acid. Well, that's not true because this number is a little bit larger. So that means ethanoic acid is actually a stronger acid because its number is a little bit larger. So that's not true. Okay, and then let's look at this one over here. The butanoic acid solution will have a lower concentration of hydronium ion. Or yes, that is true. Because the butanoic acid is a little bit weaker, because it's got a slightly smaller Ka value, it means that because it's weaker, it means that it really doesn't like to ionize. So it won't make a lot of H3O+. Who would make the most H3O+? Well, it would definitely be ethanoic acid because it's got a slightly higher Ka value. So would the butanoic acid have a lower concentration of hydronium? Yes, it would. So the answers would have to be that one. Which one of the following pairs of acids and bases, all of the same concentration, will react to give the highest pH at the equivalence point in a titration? Okay, so this question is actually all about hydrolysis. So I'm not going to go into all the details. I have got videos on hydrolysis where I explain all the different scenarios. But in summary, if you do a titration with a strong acid plus a strong base, then you will get no hydrolysis. And therefore, your pH at the equivalence point would be 7. This is all for titrations. Now, if you take a strong acid plus a weak base, then what happens is that the strong acid, you can think of it like this. You can think of, because you've got a strong acid and a weak base, then at the end, you are going to have an acidic solution. The details of that can be found in the video that I have on hydrolysis. And so because you're going to have an acidic solution, your pH will be lower than 7. That makes sense. Strong acid will always, you can think of it, they're fighting, and it will beat up the weak base. Then if you take a weak acid plus a strong base, well, now the strong base would dominate. And so at the end, due to hydrolysis, you would have a more basic solution. And so that means the pH will be higher than 7. And then lastly, if you react a weak acid plus a weak base, it kind of goes the same. It's not the same mechanism, but you can imagine if they're both weak, then no one's going to dominate. And so there is hydrolysis that takes place, but it all cancels itself out. Go watch my video on hydrolysis. I do show that. But the final pH is going to be 7. So if they want you to get the highest pH, we want a pH higher than 7, then we need a scenario where we have a weak acid and a strong base. So here you just need to know your theory. This is a strong acid. This is a weak base. Okay, so it's not that one that we're looking for. This is a strong acid and this is a strong base. This is a strong acid. This is a strong base. This is a weak acid. This is a strong base. So that's the one we're looking for. A standard galvanic cell is set up as shown below. Which one of the following combinations of the metal used as cathode and the electron flow is correct? Okay, so we definitely need to go get our table, and we need to make sure we can find cadmium and silver. I use table 4B. Okay, so step 1, we're just going to go find the reaction. So we need to find cadmium with Cd2+, so there it is over there. And then the other one is Ag and Ag+, which is over there. Okay, now, when it's a galvanic cell, remember this rule that I'm explaining now is for galvanic cells. When you're busy with an electrolytic cell, well then that uses totally different mechanisms. So when it's a galvanic cell, you can simply just look at the arrows. So if you look at this arrow, it's pointing down and it's on the left side of the table. So I want you to look on the left side of the table and find the one that's lowest down. So that would be Ag+. Okay, so you're going to go highlight that one. Then on the right side of the table, we see the arrow is going up. So it's on the right side. So you're going to look on the right-hand side of these arrows and you're going to look for the one that you've highlighted as high up as possible on the right. And so there it is over there. Okay, so now that you've got those highlighted, then I just want you to draw a line going from this one to that side, and then from this one to that side. And that is how your reactions are going to go. So the Ag plus is going to go like that. And then this one is going to start with CD. See how it starts with CD? And then it's going to end up going to CD 2 plus 2 electrons. So I've reversed this one around when I wrote it down over here, because you can't tell your teacher, oh, it's going to go like this. We're not from like some random country where we write from right to left. You got to write from left. You got to write from left to right. Okay. So you got to start the reaction like that. Okay. So these are the two reactions that are going to take place. You need to understand that when it goes from left to right like that, that is reduction. And reduction always happens at a cathode. When the reaction is written, when it goes that way around, that is oxidation. And oxidation is always where your anode is. So what metal are we going to use as the cathode? Is the cathode the Ag one or is it the CD one? It's the Ag one. So the answer cannot be this and it cannot be that. Okay, now, how is this going to work? Well, the way it works is that you're going to start with the CD. So here it is here. It's a piece of metal. And that thing is going to convert into CD2+. So you're going to start breaking some of this metal off, and it's going to convert into CD2+. And you're going to produce 2 electrons. Those electrons are going to travel through the wire. Okay, so there they travel. There go your electrons, there go your electrons, there they go. And then suddenly, those electrons travel through this metal and they arrive over here. What then happens is that this if you look at this reaction, the Ag plus combines with an electron. So it combines with an electron over here, and they convert together, they convert into Ag. And so over time, you would actually start seeing the mass of this becoming larger as you are producing more Ag. And over time, you would notice that the mass of this would actually become less because you're breaking some of it off every time it converts into CD2+. So this one's going to get smaller. This one's going to get larger. So can you see the flow of electrons? It's going from CD to Ag. So the answer is B. An electrolytic cell is set up to electroplate an iron rod with nickel. Okay, an electrolytic cell set up to electroplate an iron rod with nickel. Okay, as shown in the diagram below. Consider the following statements. Okay, so the iron rod is the negative, the metal ions undergo reduction, the anode is pure nickel. Okay, so let me just quickly draw something out for us. And let's forget about the battery terminals, for example. Let's just go put 2 electrodes. Okay, and then we've got a solution over here. Now, one of these is nickel and one of these is iron. Okay. Now, what we want to do is we want to electroplate the iron with nickel. So that means that you're going to have a piece of iron like this. So this is iron, and you're going to eventually want nickel to break off of here and then be able to travel to there. Okay? And then the nickel will go and it will go form on top of the iron rod. Does that make sense? So you're going to start with a piece of nickel. It's going to start breaking apart, and it's going to convert into nickel ions. Those nickel ions are then able to travel through the solution, and then they can react and become pure nickel again. So the point is, this iron has to be negatively charged so that it can attract the positive nickel ions that are going to be in the solution. So here's the negative terminal. So that means this one is negative. So this one should be the iron. Okay. and then this one would have to be the nickel. So it says here that the iron rod is negative. That is correct. Then it says that the metal ions in the solution are going to undergo reduction. That is correct, but let me explain. So what we have said is that this is going to be your pure nickel, and this is going to be your pure iron, Fe. Now remember that I like to always use table 4b, and remember we're not going to look at the arrows and we're not going to say which one's lower down and which one's higher up, because that is only for galvanic cells. This is not a galvanic cell. The way that it works with this one is we know that, you know, what eventually happens here is you're going to have a piece of nickel, and that nickel, which is over here, is going to have to make its way to the iron. How does it do that? Well, it's going to have to first convert into ions, nickel 2+ ions. So the reaction is going to go like that. And then those nickel 2+ ions are now in the solution, and they can then move across to the iron over here, and then they will react backwards and become nickel again. So for this part, the nickel's literally going to go that way so that it can convert into the nickel ions. Those nickel ions are then going to travel to the iron, and they are then going to react backwards and form nickel. So you're going to go forwards and backwards in this question. So it says that the metal ions in the solution, so that's going to be the Ni2+, will undergo reduction. Yes, they will, because when you go in that direction, when these Ni+2s convert back into nickel again, like over here, that is reduction. If you have a reaction that goes like that, that is reduction. So that is also true. And then it says that the anode is pure nickel. Well, we know that over here on this one, the reaction is going to be a reduction reaction, like we said. Now, reduction is always at your cathode, whether you are looking at a galvanic or an electrolytic cell. So that's the cathode. And then this one here is definitely the anode, because that is where you are going to go from nickel to nickel 2+. And that is an oxidation reaction. So all three of those statements are correct. First question here says, write down the letter that represents each of the following. So an alcohol. Okay, so an alcohol, it's definitely not going to be that one. That is an aldehyde. This one is a haloalkane. This one is a ketone. This one is... Okay, we'll come back to that one. It's definitely not this one because there's no OH. This one, it wouldn't be. It's probably an ester because you've got that C double bond oxygen. And it can't be this one. So it's either going to be D or G. So we need to just go have a look carefully. So if we look at, let's try this one, C4H10. So C4 and then 10 hydrogens. Let's see. Oopsie. That's 3 hydrogens, 4, 5, 6, 7, 8, 9, 10. How would the oxygen fit in? Oh, no, but that doesn't make sense. Okay, maybe then, maybe we take one of these away and we put an OH. Ah, that could actually work, because then you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you've got an oxygen. So D's looking pretty good. Let's see where this one falls apart. Oh, it's got 2 oxygens, of course. Alcohols don't have 2 oxygens in them. So the alcohol is going to be D. Then this one says a compound with a formal group. Now, a formal group, you know how you get like hydroxyl groups, carbonyl groups? Well, a formal group is when you have a C double bond oxygen attached to a hydrogen and then something like that. So there we can see it over there. So it's an aldehyde, which is A. Then this one says an unsaturated compound. When they say unsaturated, that's either going to be an alkene, which has a double bond, or an alkyne, which has a triple bond. It can only be one of those, okay? And when we say double bond, we're not saying double bond oxygen. we are only talking about the hydrocarbons. So it's only an alkene or only an alkyne. So it can't be that, it can't be that. We've already looked at that one. It's not that one because that's a ketone. It can't be that one because it's got oxygen, and it can't be that one because it's got oxygen. So it's going to be either this one or this one over here. Now immediately I see this CC part over there, so that makes me think there's a triple or a double bond. Let's have a look. So if we go draw this one out, it's going to have a CH3, then there's a C, and then there's a CH3, but there's two CH3s. So that means one going like this, there's a CH3, and then the other one going down. There's a CH3, okay? Then there's a carbon, and another carbon, and then a CH3. Okay, so in order to fix this thing, you would have to have a triple bond over here so that this carbon and this carbon have 4 bonds. So there we have a triple bond, and so this is definitely the answer. Okay, so then moving on, this question here says, write down the name of compound B. Okay, so step 1, find the longest continuous chain. So some learners, they just going to say, oh, it's just going to be 5. But that doesn't mean the longest continuous chain. The longest continuous chain means you can connect carbons together without lifting your pen. So for example, I could go 1, 2, 3, 4, 5 that way. I could go 1, 2, 3, 4, 5 that way. But if I go 1, 2, 3, 4, 5, 6, so that's the longest, okay? So everything sticking out is a branch. So those are branches. This is a branch, and that is a branch. These are not branches because they're on the main chain. So I know it's a halo alkane. I know it's got 6 carbons, so I can immediately say hex. And I can say hexane because that is how I end off the wording, or the end of the word for halo alkanes. But now for this beginning part, I need to include all the branches. But now I want my branch numbers to be as low as possible. So if I start, remember with halo alkanes, you don't have to start from the side that is closest to the halogen. They are like a weird exception. So if I started over here, this would be carbon 1, 2, 3, 4, 5, and 6. So you would have branches on carbon 3 and carbon 3 again, right? And then on carbon 4, you would have 2 branches, so 4 and 4, because you've got one here and you've got one here. If instead you rather labeled it from this side, then your branches would be on carbon number 3 and 3 because of this one over here, and then also on 4 and 4. So this is something we don't see too often, where if you name it from the one side or the other side, your numbers are the same. So what do? Well, now we go to another rule, which I haven't really ever had to mention, because to be honest, this hardly ever happens. But what you need to do in a situation like this is you need to now base it off the alphabet. So we've got bromo, which are these branches, and then these branches here are methyl branches. Methyl. So what comes first alphabetically? Well, B for bromo. So we are going to label it from the side that lets the bromos have the lowest numbers. So we're going to label it from the right hand side, where the bromos will be the 3s and the methyls will be the 4s. Okay, so that's quite interesting. So on carbon 3, there are 2 bromos, so we're going to do that. And then on carbon 4, there are 2 methyls, so we're going to do that. And then hexane. Now normally we always put the bromo before the methyl anyways, so that is correct. We always do that. But then Kevin, what are you talking about putting the lowest numbers? Well, if you labeled it from the other way, then you would have got the following. You would have got this, and it's wrong. You would have got 4,4 dibromo. So you see how we would still put the bromo first, because it's alphabetically before methyl. But in this scenario, you're now giving the smaller numbers, or you're giving the bigger number to the one that comes first alphabetically. And what we said was that when you have an absolute tiebreaker where you have 3, 3, 4, 4 and 3, 3, 4, 4 for the other one as well, then you want to give the smallest numbers to the alphabetical one that comes first. Okay, which is something we don't see very often at all. In fact, I don't think I've seen a question where they've asked it like that before. Okay, now for this one, they want us to get the name of E, which we had drawn out earlier, but let me just quickly go do it again. So we've got CH3. Then we had a carbon with a CH3 going this way, and then going this way, and then C, C, CH3. And we then said that there was a triple bond over here. Okay, so to name this one, we first look for the longest continuous chain, which is just going to be 1, 2, 3, 4, 5. So that's going to be pent. And we can see that we have a triple bond. So we have to honor that triple bond, and we name it from the side that's closest to that triple bond. It's not the same as a haloalkane. With a haloalkane, you don't really have to label it from the side closest to that. You rather look at the branches. But when it's another functional group, like a triple bond, a double bond, like an alcohol, then you name it from the side closest to the functional group. So we will start our naming at carbon number 1. And on carbon number 2, we have a triple bond. So we do that. Okay, so we name from carbon 1. So what we'll notice is that on carbon 4, we're going to have a methyl up here and a methyl down here. And so on carbon 4 and 4 again, we're going to have 2 methyls. So we're going to say dimethyl. Okay, now this question. 2 different compounds in the above table are functional isomers. Okay, so in grade 12, we've only got 2 sets or 2 pairs of functional isomers. Those are going to be ketones that go with aldehydes. And then it's going to be carboxylic acids that go with esters. Okay, so we definitely did have an aldehyde and we definitely did have a ketone, but are they the same carbon number? Well, this one is 1, 2, 3, 4, and this one is BUT, that's also 4. And so they would definitely be functional isomers, but let me prove it to you. If I had to draw butane 1, it's a 4-carbon molecule, and it would have a double bond oxygen. Now remember, because it's a ketone, the double bond oxygen cannot be on the last or the first, the first or the last carbon. It'll always be one of the middle ones. So we go there like that. And then the rest is all hydrogen. And if you had to now go count all of the carbons, you would get 4. All of the hydrogens, you would get 3, 5, 8, and then 1 oxygen. If you had to now look over here, there's 4 carbons, 3, 6, 8 hydrogens, and 1 oxygen. So it's exactly the same molecular formula, but different functions. This one is an aldehyde, whereas this one is a ketone. So we call those functional isomers. So maybe Kevin should read the question. First question, define the term. And then for this one, write down the letters. Okay, so we can actually just fill in the letters so long. It's A and then C. And then what is the term functional isomer? Well, let me explain. I will go get the definition now, but let me just explain. So functional isomers are molecules which have the same molecular formula. You see how we have the same molecular formula, but different functional group. Okay, so in this one we had an aldehyde, whereas in this one we had a ketone. So the actual definition, compounds with the same molecular formula, but different functional groups. Okay, and then that's obviously just the Afrikaans one. Okay, cool. Compound F is formed when the carboxylic acid reacts with another organic compound in the presence of a catalyst. I don't know about you, but this sounds like esterification, because we know that they love to ask this. Whenever you take a carboxylic and you react that bad boy with an alcohol, it always leads to the formation of a ester, and they love asking this. They also love isomers. So if I was you and you're busy studying and you have a bit of time, make sure you understand isomers and you understand the production of esters from a carboxylic acid and an alcohol. I see that over and over and over again. Right, so compound F is formed. Okay, so compound F, what are you? You're an ester, because look, C double oxygen, or C and two oxygens like that. That is only found in esters. If it was a carboxylic acid, you would see a COO with an H. There's no H over there. And carboxylic acids, yeah, it would typically be at the end of the molecule, whereas here we've got it like in the middle. So that's more indicative of an ester. Okay, so it's definitely that thing that's going to be. Now it says write down the name or formula of the catalyst. You can just use H2SO4, or you can call it sulfuric acid. Now, what is the type of reaction? Well, it's going to be esterification. And then what is the structural formula of compound F? Well, we can just go check it out. We don't need to go do the whole reaction. So it's got a CH3. It's then got the COO, so it's going to be a C with an O over there and a double O over there. You need to understand your organic molecules. That's why that would be so easy to figure out like that. And then we've got a CH2, but there's two of those. So there's going to be a CH2, which looks like that, and then another CH2, which looks like that, and then a CH3, and then they just want the name of compound X. Okay, so let's just check. Compound F is formed when a carboxylic acid reacts with another compound X. Okay, well, we know that a ester is comprised of a carboxylic and an alcohol, and we know that this is the carboxylic part, and then this is the alcohol part. Okay, the carboxylic is always the one that has this double bond oxygen. Okay, so they said compound F is formed when a carboxylic reacts with another compound. Okay, so the carboxylic is this one, and then the another compound is going to be this one over here. So what is its name? Well, simple. It's a 3 carbon, so that's prop. And then we can see, if this was the alcohol, obviously it would have had a little OH over there. We can see that the alcohol part is on carbon number 1, so we're going to say propan 1-ol, like that. The vapor pressures of different organic compounds have been determined at 20 degrees. The vapor pressures of compounds A, B, and C are not shown in the table. Okay. First question, define the term vapor pressure. Right, so like always, let's first talk about vapor pressure so we can have a nice idea of what it means. So let's say, for example, we have a pot of water on a stove. Okay, so here we have our water. So let's just say we've got some water molecules over here. Okay, and what will happen is that, and let's say we have a lid. Let's say we have a little lid over there, and let's say we have a little device over here, and that device, what that device measures is the pressure in the air over here. And then let's say we have another little device out here, and this measures the pressure in the atmosphere. So like in the room, in the house, for example. So this is the atmosphere. And then this would be like the little area inside the container. And so what happens is that if we begin to apply some heat, so let's say we put the stove on and we apply some heat, so here's like a fire, then obviously some of these water molecules are going to turn from liquid into gas. So they're going to end up going into the area over here, right? And so eventually, we've got a whole bunch of water molecules here, and some of those are going to evaporate, and they're going to end up going over here. Whoops, I just erased everything. So remember that this area here is not water. This area here is, well, it's not liquid. It's gas. whereas this area here is liquid. So as you produce more and more gas over here, the pressure that this system registers is going to go up, right? Because you're going to have more gas molecules. Sorry, we don't actually need this one. That's for a different definition. I was thinking of boiling point. So this pressure is gonna keep going up, keep going up, keep going up, and eventually we are gonna reach equilibrium. What that means is that the rate at which we go from a liquid to a gas is going to be the same as the gas turning back into a liquid, okay? Eventually you reach an equilibrium. At that point, we would look on this little device and we would read out the vapor, or we would read out the pressure, okay? So when we have a liquid that is in equilibrium with its gas in a closed system, then the pressure that the gas has, we're going to call that vapor pressure. So let's go get the definition now. So vapor pressure is the pressure exerted by a vapor which is at equilibrium with its liquid in a closed system, just like we explained over here. Okay, then it says that the vapor pressures of compounds A, B, and C are given in a random order below. So it doesn't mean that this is A and this is B and this is C. It's a random order. So this could be A, this could be B, and this could be C, for example. Okay, so it says write down the vapor pressure for compound C. So, okay, now we need to go talk a little bit about how vapor pressure actually works based upon what the type of molecule is. So, just listen very carefully to what I'm going to say now, guys. So let's say you have a liquid of some type of substance. Okay, so we've got a liquid. And let's say we've got these molecules. Now, each of those little things could be like a big molecule, like a pentane molecule, for example. Now, these liquids are floating around. Life is good. And what we must understand is that they are being held together slightly due to intermolecular forces. Okay, so there are intermolecular forces between molecules. Now, if you want to start causing some of those liquid molecules to go into the gas phase, well, you are going to have to be able to overcome these forces that are holding them together. And to be able to do that, you're going to require energy. Okay? So that should make sense. You need energy to be able to overcome these forces so that these molecules can then go into the gas phase where they will then be able to spread out a little bit further. Okay, so to be able to get them to spread out further like that and to get into the gas phase, you need energy to overcome these forces because these forces are attracting the molecules together. So if a substance has very, so let's write this out. If a substance has strong intermolecular forces, so think about that. If these forces are very strong, is it going to require, will we need more energy or less energy to get them into the gas phase? Well, we would need more energy. More energy would, or let's just rather say, it is more difficult to overcome the intermolecular forces. So, if you have situation, so let's say we've got substance A, so this is all for substance A, let's just call this substance A, and then we've got another scenario where we've got substance B. Okay, so let's draw in the liquid phase. Boom, boom, boom. And then let's put our little lid on like that. Okay, now let's say this is substance B. Now we already said that substance A, let's say that substance A has strong, oh, and by the way, when I say A, I'm not talking, okay, let me rather change this up. Let's say we've got substance Z and substance W. I'm not talking about these. I'm still explaining. So let's say these are very strong, but let's say in this substance, the intermolecular forces are very weak. Okay, so then let's say, so obviously because these are weak, will it be easy or difficult to get them into the gas phase? It'll be very easy. So let's say both of these containers are next to each other in a room once upon a time, and let's say the temperature in the surroundings is 20 degrees, like they've told us. That 20 degrees is a form of energy, heat energy, okay? So with that 20 degrees, do you think we will be able to create more vapor with this system over here or with this system over here? Which one is going to be easier to separate those liquid molecules and turn them into gas? Well, this one over here. So with 20 degrees of energy or temperature, we will be able to convert more of these molecules into the gas phase. So which of these situations would we have a higher vapor pressure? Well, in this one, you would have a much higher vapor pressure. Higher, because more of the molecules are going to be turned into vapor. So what we can then see is that what we can make a summary, and that is intermolecular force strength is inversely proportional to vapor pressure. What that means is that when the intermolecular force strength is very high, like in this situation over here, then the vapor pressure will be very low because there's less molecules that are able to go into the gas phase. Conversely, when the intermolecular forces are very weak, like over here, then or very low, weak, that's what I meant, then the vapor pressure will be very high. So you see how they are inversely related. So what we need to then go and do now is go look at these three molecules and try think about their intermolecular forces and try rank them according to whose intermolecular forces are stronger or weaker. And then from that, we can use the inverse relationship with vapor pressure to try work out who's who in the zoo, because these are all different pressures over here. Okay, so all that I want you to understand, this is like a little overreaching summary. Intermolecular force strength is inversely proportional to vapor pressure. So when the strength is high, vapor pressure is low. When the strength is low, vapor pressure will be high. So let's make that summary quickly. When intermolecular forces, or the strength, is high, vapor pressure is low. When intermolecular force strength is low, vapor pressure is high. Vapor pressure is high. So they have an inverse relationship. Inverse relationship. Okay, so what we are going to go and do now is we're going to go look at pentane, 2-methylbutane, and 2,2-dimethylpropane, and we're going to go investigate the intermolecular forces to try see which ones are stronger and which ones are weaker. And here we are. So let's go, we'll do this, and we'll do that. So let's look at pentane. Now remember, whenever we look at intermolecular forces, we're always going to go draw two of the molecules. Right, so if we look at the intermolecular forces, I'm not going to go into all the details, but we should know that the only intermolecular forces between these two would just be London forces. Okay, London forces. There's no dipole-dipole, hydrogen bonding, none of that. Now, if we go do 2-methylbutane, that's going to be a butane molecule with a methyl on carbon 2, and then obviously all the hydrogens. Okay. And for those of you that understand your work quite well, you're going to notice that every single molecule we are going to draw is going to be, there's just going to be London forces. So how are we going to actually categorize it? Well, don't worry, we're going to get to that. There is a reason, there is a way we're going to do it. Okay, so once again, these kind of molecules, simple alkanes, no dipole-dipole, no hydrogen bonding, so it's also just going to be London. So there's intermolecular forces. It's also just going to be London. Okay. And then if we go draw 2,2-dimethyl propane, that would be a propane with a methyl on carbon 2 and carbon 2 again, like that. Okay. And then once again, if we look at the intermolecular forces, it's going to be London forces again. So we've got London forces in all of them. So what are we going to do, guys? How does this work? Well, what they are getting at here is how do branches affect intermolecular strength? So, well, how does it affect the London strength? So you can see we've got branches over there. And then on this one, we've got, we've got multiple branches over there. So what we've learned is that branches decrease the surface area of the molecules, For example, over here where you've got absolutely no branches, you see there's a lot of surface area that's available. Okay, you can see there's quite a bit of surface area. But as soon as you start going with branches, I don't know, the amount of available surface area, if you could measure it, scientists have been able to show that the available area becomes less. Okay, so the more branches you have, the less available area there is. So let's just say here, to make it even more clear, to make sure we really understand, the more branched a molecule is, the lower its surface area. Let's write that a bit better. Okay, now if you have a lower surface area, like for example over here, if there's less surface area, then there's less area where the London forces can operate. Okay, so here on this one, you can have loads of London forces. There. And, it just ends up causing the London forces to overall be much stronger. Whereas here, there's less surface area available, so it causes the London forces to not be as strong. Now, when you have less surface area available, like over here, for example, then there's less areas where the London forces can act. Like in this one here, there's lots of areas where the London forces can act. Whereas over here, it's a little bit more tricky. Like, it's difficult. It's there's not as many. There's less surface area, so there's less areas where London forces can actually operate. Okay. So we could say something here like, with less surface area, there will be less London forces. Okay, so I think you get the idea, right? So if we now go back to these molecules over here, we should then be able to understand that with pentane, there's going to be a lot of area for London forces. So these intermolecular forces are going to be very strong. So pentane is going to have the highest intermolecular force strength, okay? Then this one is going to be in between because it's got one branch per molecule. So this would be medium. And then this one over here with two branches per molecule is going to have the smallest or the lowest surface area. So it's going to have the weakest of those London intermolecular forces, okay? So if we now come back to here, if pentane has the strongest intermolecular forces, then it should have the lowest vapor pressure. Remember we said vapor pressure, or what we said here, when the intermolecular force strength is high, vapor pressure is low. So the one that has the highest intermolecular forces out of these three should have the lowest vapor pressure. So this should be pentane. This one would then be 2-methylbutane. And then this one is going to be the 2,2-dimethylpropane. So they said write down the vapor pressure of compound C, which is that one. So it's going to be this one over here, which is going to be 146. So we can just fill it in there, 146 kilopascals. And then fully explain your answer to the question. So we can say something like, for 3.2.2, we can say compound C is the most branched molecule out of A, B, and C. Okay? Then for our next point, we could say compound C will therefore have the lowest surface area, which results in less London forces. You are also allowed to say intermolecular forces there. And then, so from all of that, now we make the conclusion, less energy needed to overcome forces of attraction. And then you should squeeze in here, let me just write it again for you, in compound C. So they don't expect it, but you could also add, therefore it would have the lowest boiling point, and therefore it would have the highest vapor pressure. They didn't expect you to do that. They just wanted you to give the basics of why the intermolecular forces are so weak. And yeah, there we go. Okay, now we're moving on to here. It says that compounds D and E are compared. Okay, so we've got a propanonic acid and a butanol. So this is a carboxylic acid. This is an aldehyde. Now it says which compound has the lower boiling point. Well, what you do is you look at the vapor pressure. And remember what we said is that boiling point. Okay, well, we didn't really talk about boiling point, but we know the following. We know that high boiling point, if something has a high boiling point, it means that it has very strong intermolecular forces. And we know that if something has strong intermolecular forces, then it's going to have a very low vapor pressure. Okay, and then if something has a very low boiling point, then it's got weak intermolecular forces, and so it would have a very high vapor pressure. So if we look at these vapor pressures, we can see that the one that's going to have the lower boiling point is going to be the one with the higher vapor pressure. So this number is the highest number. So that one is going to have the lowest boiling point. So we can just say E. And then this last one says, explain the difference in the vapor pressure. So you can just say that compound D has a vapor pressure of that, and then you can say compound E has a vapor pressure of that. Okay, that was a joke. Obviously, for 4 marks, they're not gonna accept that. So what we'll do is let's go do a proper analysis on compound D and E. Let's go look at their structures. Let's talk about their intermolecular forces. And once we know about their intermolecular forces, we can then comment on why they have a difference in vapor pressures. Okay, so let's go compare them now. So for propanonic acid, I'm just going to say propanonic. Let me just write the whole thing. Okay, so we know that prop means 3, and we know that it's a carboxylic acid, so it's got the double bond oxygen with an OH, like that. And then obviously everything else is going to be hydrogens. And we're now going to go draw another one, because whenever we are looking at intermolecular forces, we are looking at the forces between the molecules. So we need at least 2 of them so we can understand what's going on. Okay, so that's propanonic acid. And then butanol is going to be a 4-carbon molecule. This means it's an aldehyde, so it's got a double bond oxygen that is on the side. Remember, aldehyde, double bond oxygen on the side. If you've heard me say that before, you know you know. You're an OG. H. All right, mateys. So let's quickly go compare. So we know that in these areas here, that is just going to be London forces. Okay, that's just going to be London. Same as, like this area here. All of that actually is just all London, that area there. Okay, and the same with this over here. Boom, pretty much just London forces. Okay, so they equal there. Then if we look over here, this is a polar part of the molecule. This is polar, and this area is also polar. So this area here, the intermolecular force between that area there would be dipole-dipole. But then we get to this area here, which together with that area is going to be a hydrogen bond, which is very strong compared to London or dipole-dipole. Okay, so those were dipole-dipole, and then we've got a hydrogen bond. Now, if we look at this molecule, we've said we've already got the London, and then you're going to have a polar section over here, and a polar section over here. So the intermolecular force over there would be a dipole-dipole. Okay, so we can see that, the big elephant in the room is the fact that propanonic acid has a hydrogen bond, whereas butanol doesn't. That is the main reason why propanonic acid has such a lower vapor pressure, because it's got much stronger intermolecular forces, right? Because remember, the intermolecular force strength and vapor pressure are inversely proportional. Okay, so the way we're actually going to answer this is the following. We're going to start off, because it's one of these 4-mark questions, we're going to do the following layout. We're going to mention the strongest intermolecular force in the first molecule, whether you want to do propanonic acid or butanol first, it doesn't matter. Then you're going to mention, and that'll get you 1 mark, then you're going to mention the strongest intermolecular force in the second molecule. That'll get you another mark. Then what you do in your third step is you then compare those 2 intermolecular forces together. So compare the above intermolecular forces and then conclude. That is how you get your 4 marks in these types of questions. So for step 1, I'm going to start with propanonic acid. So I'm going to say propanonic acid. Whoa, what's going on? Propanonic acid has hydrogen bonding between its molecules. You are also allowed to, if you want, mention that it also has dipole-dipole and London forces. You don't have to. What they're looking for is that you mention the strongest one. In our next step, we're going to mention the butanol. And we saw that that one has dipole forces between its molecules, and then say therefore oh, by the way, and I wanted to mention this earlier. Some of you might be like, yeah, but Kev, how can we make a comparison between a 3-carbon molecule and a 4-carbon molecule? Yes, I get it. If they didn't give us the vapor pressures, then we wouldn't really be able to compare them. We can't really tell whether maybe because this one is longer, maybe this one would have stronger London forces because it's longer and it's got a larger surface area. So then it wouldn't have been a good question if they didn't give us the vapor pressure, because then we wouldn't really be able to compare them nicely. Okay, because this one is a longer molecule, it's got 4 carbons, whereas this one has 3. So even though this one has hydrogen bonding, this one might have still been the stronger intermolecular forces because it's slightly longer, so it's got a larger surface area. But because they gave us the vapor pressures, we can read off and actually see who has the stronger and who has the weaker intermolecular forces because of these relationships up here. Okay. Now, then we can say, therefore, the intermolecular forces, in compound D are stronger than in compound E. And then this last fourth step is always the same for these questions. You can say, therefore, more energy needed to overcome the forces of attraction in molecule D. They don't even on the memo expect you to explain this relationship over here. You don't even have to then go say, therefore, molecule D would have stronger or higher boiling points, and therefore it would have lower vapor pressure. They don't expect that. They just kind of assume that you already know that. So you just have to go do this 4-step process over here. If you did have to go add all that extra information like this, they're not going to mark you down. You're just adding extra info, but they definitely won't give you bonus marks. Reaction 1 is a cracking reaction, okay? So reaction 1 is over there, forming 2 organic compounds, W and T, as the only products. Okay, now I'm going to just split the questions up onto different pages, actually. So here we've got that, and then we've got that. Okay, so this one says, define the term cracking. So let's talk about what they do cracking for in real life. So in real life, we get these very long alkane molecules, okay? So maybe they're like super long like that. And then obviously there would be hydrogens everywhere. Now, these longer molecules which we find in real life, they're not very useful for a lot of applications. But what is very useful is often to have much shorter compounds. So cracking is the process where you take these longer chain alkanes and you break them up into shorter chain molecules. And so it's the chemical process, or you can use the word reaction, where a longer chain hydrocarbon, or an alkane you can say, are broken down into shorter molecules. 4.2 is the product in reaction 2. Okay, where's reaction 2? Here it is here. Okay, so is the product in reaction 2, which is over here. So here's the product. Is it a primary, secondary, or tertiary haloalkane? So we're going to have to just draw it out quickly. So it's got a CH3, then it's got a CH2, then it's got another CH2, then it's got another CH2, and then it's got a Br. So to work out whether it's primary, secondary, or tertiary, all you do is the following. You locate the halogen. So, and you can do this with alcohols as well. So there's the halogen. Then I want you to highlight the carbon that is touching that halogen. There it is. Then I want you to count how many carbons are touching that carbon. Well, that would only be 1. Don't say 3. These two over here aren't actually touching this carbon. If you had a carbon there and a carbon there, then you could say 3. But physically touching this carbon, there's only 1. So if it's 1, you say primary. If it was 2, you would say secondary. And if it was 3, you would say tertiary. So where are we? We are going to say it's a primary. And then you can literally say the carbon atom bonded to the Br is itself bonded to one other carbon. Okay, now moving on to this question here, says write down the structural formula of compound W. Okay, compound W. Okay, so we know that there was originally this organic compound U, and it underwent a cracking reaction, and one of the products was C4H8. Okay, so one of the products is C4H8, and then the other product is W, which we don't know what that is. However, we should identify. You can go draw this out if you want, but this is an alkene. How did I know that without drawing it? Because I see it's got the CnH2n, because 4 is half of 8, or 8 is double 4. But if you had to go draw it out, you would also see that it has to have a double bond. Now, something I didn't mention earlier when we were talking about cracking is that the products is often going to be an alkene, and then the other one will be an alkane. Okay? So if we already have the alkene over here, then this one would have to be an alkane. And you're not going to get two alkene molecules when you crack. It's going to usually produce an alkene and then an alkane. So to then work out what alkane this is, we can actually just look at this reaction. We can simply count how many carbons we have over here, and we can see 1, 2, 3, 4. So that means we would have had to have a 4-carbon alkane over here. So a 4-carbon alkane would look like that, and then it would just have hydrogens everywhere, because that's what alkanes have, right? There we go. And that would be your structural formula that they're looking for at 4.3.1. Now, they say over here, what is the molecular formula of the original compound U? Okay, so then what you're going to do is you're just going to look at this one, which we said was a 4-carbon molecule, and you're going to look at this one, which is a 4-carbon molecule. So then this one would have to have been an 8-carbon molecule, and we know that cracking is when you crack alkanes, so it's literally just going to be an 8-carbon alkane. Now, they don't want the 1, 2, 3, 4, 5, 6, 7, 8. They don't want the structural formula. Now they just want the molecular formula. So there's going to be 8 carbons. Now, if you understand your general formulas very well, you can immediately work out that there should be 18 hydrogens. How did I do that? Because I know that for alkanes, their general formula goes like this. So if I have 8 carbons, then I would have 2 times 8, which is 16, plus 2, which is 18. If you don't know that, you could go fill in all of these hydrogens, you would go count it all up, and you would get 18 hydrogens. For reaction number 2, where's reaction number 2? Okay, the one we've looked at already. Write down the name or formula of the inorganic reactant. Okay, so what they mean by that is, we know that this over here was an alkane, which was C4H10. Now, they want to know, what did you react that with to be able to produce this? So if we look at C4H10, if we just draw it out quickly, and then if you look at the product, it's a CH3, a CH2, another CH2, another CH2, and a Br. So they want to know, what would you have reacted it with over here in order to make that? So we definitely needed a Br. But now remember that Br is a halogen, so it's typically, diatomic, so you're going to get it as Br2. So you'll react it with Br2, like that. So that is the name of the inorganic, or the name or formula. So you could say bromine, or you could say, you could write out the formula like that. Now it says, what is the type of reaction? Substitution, addition, or elimination? Well, all that's happening is that we are simply going to knock this one off and replace it with that one. So we're not going from like single bonds to double bonds, or double bonds to single bonds. So this is just going to be a normal substitution reaction. And then what is the reaction condition? Well, one of them is that this is the one where we will typically, you need energy in the form of UV. So you would say UV light. Okay, moving on. So 4.5 says write down the type of elimination reaction in reaction number 3. So reaction 3 is this one over here where we are going from this to this. Okay. Oh, it's actually very easy. I was thinking like, how do we know? Because there's so many different types of elimination reactions. There's dehydration, dehalogenation, dehydrohalogenation, for example. But it's easy because if we just go draw this out again, we know that we've got a CH3, CH2, CH2, another CH2, and a Br. So there is only one scenario, and that is that we are going to eliminate the Br, of course. So that carbon has already been taken care of, and then we don't even have to worry about Zaitsev's rule, because Zaitsev's rule would only have come in if this carbon was like somewhere in the middle. For example, if we had something like this, where the Br was here, then what would then happen is that we would lose this Br, and then you would have to figure out, are we going to make the double bond here or here? And to do that, you would have to work out, are we going to lose a hydrogen here or here? But when your carbon that is losing the Br is already on the end of the molecule, it's the very last carbon, then the only other carbon is the one next to it, because you have to form the double bond over there. So you can't form a double bond here, for example, because that's not where the Br was lost. So we know for 100% surety that we're going to lose that Br, and then on this carbon here, it's going to lose one of its hydrogens. Whether you want to do the top or the bottom, that's your choice. I'm going to choose the top one to lose. And so that is what this molecule is actually going to look like, this one over here. And so what did we do? We got rid of a halogen as well as a hydrogen. So it's going to be a dehydrohalogenation. Because we got rid of, that's what the D stands for, hydrogen and halogen. So we're going to say dehydrohalogenation. You know what I was thinking about today, guys? In my next life, I want to be a fly. Because when a fly walks into a room, everyone waves at it. Like, I was sitting at a place today. Well, I'm trying to pretend like I'm social. I was actually just at home by myself. And I had a piece of meat on my plate. And as soon as I'm sitting there and this little fly lands on it, I started waving at the fly. And I think back now to like times when I've been with other people and we've been at like a braai or we're sitting somewhere. As soon as a fly comes into a room and it like chills on the food, everyone starts waving at it. So in my next life, I'm going to be a fly because everyone loves them and everyone waves at them. And yeah, so that was my aha moment today. And you might think I'm crazy, but the next time you're sitting around with people or you have a piece of food or some food in front of you and a fly lands on it, watch what you're going to do. Just watch. Now, this question says that compounds R and T are positional isomers. Where are R and T? Okay, so here's T and here's R. Okay, we already drew out what this compound is. Let's just do it again. So we already said that it looks like this. With a double bond there, and then all of these are hydrogens. Okay, so we already know that this is what R looks like. So it says that R and T are position isomers. And okay, I'm actually nervous to even look at this stuff. So let me quickly just talk to you a little bit about what positional isomers are. So positional isomers means that they are the same functional group. So positional isomers, first of all, are isomers, okay? So positional isomers. So they are definitely isomers, and isomers are molecules with the same molecular formula. So for example, if this one is C4H8, then this one would also be C4H8. And if you want to go check me on that, you would see that there are 4 carbons and there would be exactly 8 hydrogens. Now, what is a positional isomer? We'll say, but different position of the functional group. So this functional group is the double bond, which is currently on carbon 1. So with this one, it's probably going to be on carbon 2. Or it'll have to be on carbon 2. So it would be more like that. Okay, so that is what this molecule looks like. It's going to have its double bond there instead of there. Okay, so let's just quickly remind ourselves about that. So it's going to look like that. And then obviously hydrogen. Okay, this part here is a little bit weird. This is the part that puts me off. The organic reagents shown below are available for reactions 4 and 5. Okay, whatever. Okay, so this question says, write down the balanced equation for reaction 4 using structural formula. Okay, so, and we got to use these as well. Not all of them, but, you know, they've given us some things we may use. So technically, when you have an alkene over here, they undergo addition. So you're gonna do addition over here. And then you're going to have some molecule here that then has to be converted back to an alkene again. So this is going to be elimination. Okay. Now, you could technically, add onto this alkene, you could definitely add Br2, you could add HBr, and you could add hydrogen. So how do we know which one's correct? This question is a little bit weird because it doesn't make it super clear. There is a way we're going to do it, but it definitely could have caught some learners. So let me start by saying why we won't use this one. Because in order to add hydrogen to a alkene, you need nickel or palladium or a platinum catalyst. And I don't see them add any of those over here. You might say, Kevin, but they're not showing any catalysts over here. They're just showing the reagents. That's what I thought. But then they're also giving us H2SO4, which is always used as a catalyst. It's never a reagent. So if they wanted us to use hydrogen, I would imagine that they would have put here platinum, palladium, nickel. Okay? So we're not going to use hydrogen. We're also not going to use Br2. The reason is, if we did add Br2, then you would end up having a Br added here and a Br added here. So compound S would then look something like this. You would have a Br over there and a Br over there. Now in grade 12, we don't really look at the reaction where you go from having 2 halogens to going to an alkene. We typically only look at scenarios where we have 1 halogen. Okay, so that's why we also won't use that one. But it wouldn't technically be very wrong, and that's the part that irritates me a little bit about this question. But we definitely then can go and use that one. So we're going to add some HBr. So let's go write out what we have at compound R so long. We've got that over there, and then the rest is obviously all hydrogen. Okay, and then we're going to add HBr. And then to work out your products, well, here's where we're going to use Markovnikov's rule. So, you know, the richer get richer and the poorer get poorer. Well, now we're doing addition, so we're going to focus in on this part, and this part is not relevant. So how do we know where the hydrogen is going to go? Is it going to go there or is it going to go there? Well, what Markovnikov's rule tells us is that the richer get richer. So if you look at this carbon, how many hydrogens does it have? It only has 1. If you look at this carbon, how many hydrogens does it have? It has 2. So this one is the richest in hydrogen. So the rule says that this one will become even richer. So we're going to add the hydrogen there, and the Br would go to the other place. So now when we show that at the product, we will have the Br over there, and then the hydrogens. And that is it for that one. Just remember that when we move to the next part of the questions, this is compound S. Okay, so that's this one over here. Okay, so now we can move on to this one. It says, what is the balanced equation for reaction number 5 using structural formula and the correct reagent shown above? Okay, so at organic compound S, we've got this one over here. And we need to convert that back into an alkene. So very easy. We know that we're going to eliminate this over here. and then we'll just use Zaitsev's rule to work out if we are going to lose the hydrogen over there or if we're going to lose the hydrogen over there. Okay, so I've just gone and redrawn compound S over there. Right, now we need to talk a bit about how we're going to do this reaction. So we know that we can convert a halo alkane, which is what we have here, to an alkene. We know that it's an elimination reaction. And we know that to do it, you have to use concentrated, strong base, like KOH or NaOH. If we use dilute, then it rather goes to a alcohol. Remember that. So this is that part where if you use concentrated, you go to an alkene, and if you use a dilute, then you go to a alcohol. Okay, so here they've given us the concentrated strong base. We know NaOH is a strong base. And so we're going to use that as a reagent. Now, you've maybe seen my video where I explained that in some schools, they treat this like almost like a catalyst. And then in other schools, they treat it like a reagent. So they would put it as a plus NaOH like that. Now, for some reason, the memo only shows this method over here, okay? But I have seen that some textbooks and some schools, they rather use the method where you have NaOH as a almost like a catalyst in a way. But I'm just going to do the method where we treat it like a reagent. And so what happens is that we are definitely going to eliminate this Br over here, okay? And that would actually eventually go and link up with this Na. And then we're going to lose a hydrogen. But now we need to use Zaitsev's rule. So remember the riddle, the richer get richer and the poorer get poorer. Now, because we are doing elimination now, we're not going to focus on this one. We're rather going to focus on this part here, which is Zaitsev's rule, which says that the poorer get poorer. So what you're going to do is you're going to look at the carbon on the left and the carbon on the right, and you're going to see that this one has 2 hydrogens, and this one has 3 hydrogens. So who's the poorest in hydrogen? Well, that would be this one. So the riddle says that the poorest one will get even poorer. So we're going to lose our hydrogen over here. So let's say, for example, that one over there. Whether you chose the top one or the bottom one doesn't matter. And so what happens is that that hydrogen is going to link up with this OH. So the different products we're going to get this over here, with this part has now been removed. And then this part has now been removed. So we just have that. And we have that. So in order to fix this molecule, we're going to put a double bond over there, and that makes sense. It's exactly what we were expecting. And then the other 2 products will be the Br is going to link up with the Na, so you're going to form NaBr. And then the OH is going to link up with the H, and you're going to form H2O. If you did the other method that some schools and textbooks use, where you rather show it like almost like a catalyst, then you wouldn't see these in the product. Instead, in your product, you would just see, that these 2 would combine. And so your product would only have this, and then you wouldn't have these 2. Instead, you would have HBr as a combined product like that. Okay. Now, what else? The balanced equation, using structure and the correct reagent. There we go, done. And then lastly, what is the IUPAC name of compound T? So this is compound T over here. That's a simple one. That's a 4 carbon. It's an alkene with double bond on carbon number 2. So you're just going to go like that. And then there's no branches. And so that is it. Here are all the questions we will be doing for question 5.1, but I'm going to break it up just so we have a bit more space. Okay, so the reaction between pure aluminium and excess hydrochloric acid is used to investigate the factors that affect the rate of reaction, the balanced equation, is given over here. First question, define the term reaction rate. So before we get the definition, reaction rate, the word rate just tells you how quick. So reaction rate is how fast a reaction takes place. That's not the formal definition. Here's the formal definition. Okay, so there we have it. I typically use these ones over here, the first two, where it's the change in concentration of product or reactions per unit time, and change in moles or of product or reactants per unit time. Okay, so you want to include the words change in concentration, and then you can just say product or reactants per unit time, or you can do change in I like to use change in number of moles of products or reactants per unit time. Okay, so moving on, they tell us that in experiment 1, 1 mole per decimeter -3 of HCl reacts with 0.5 grams of aluminium at room temperature. The graph of hydrogen versus time is shown below. Okay, let's just talk about that. So we've got some HCl that they've given us and some aluminium. Remember that the HCl is the excess. So that means that the reaction will stop once we have used up all the aluminium, of which they have given us 0.5 grams. And we can see that hydrogen gas is a product, and that is what they are showing us over here, the volume of hydrogen gas. So as the reaction progresses, the amount of hydrogen gas would increase, and eventually it would stop increasing and it would remain flat, and that would be when the reaction is finished, and that would be because aluminium has been used up, because it is the limiting reagent. So they say for the time interval from t equals 0 to t equals to 5, okay, so just this little area over here, the average rate of the formation of hydrogen gas is 0,0, now check this carefully, 0,033 decimeters per minute. So if we know that this reaction up till there is 5 minutes, then we could easily work out how much volume of hydrogen gas we've produced, because they told us that we are producing 0.033 decimeter cube, that's a volume, every minute. So if you simply multiply that by 5, you will be able to see how much we produced in 5 minutes. Calculate the mass of aluminium present in the container at t equals to 5. Take the molar gas volume as 24,5. Okay, so what we're going to do is, this is a gas, so we're going to say 0.033 multiply by 5, and that, I'm not going to round it off, that's going to give us 0.165 decimeter cube of H2 produced. Okay, so now we know how much hydrogen we produced. We can then use this formula over here. Okay, normally we would use 22.4, but that 22.4 is only when you are at STP, standard temperatures and pressures, but maybe this experiment is not taking place at STP, so they've given us a different molar gas volume that we should use, and that is 24,5. So we are rather going to use 24,5. So we can then work out the moles of hydrogen gas, because we know the volume of hydrogen gas that was produced, 0.165 in the 5 minutes, and the molar volume is 24.5, not 22.4, because we probably are not at STP. They would have told you if we were at STP. Then you would have used 22.4. Okay, and if we work this out, we get 6.734, I'm going to round to 4 decimals, times 10 to the -3, and that is moles. From that, we can now come back to this equation, and we've just worked out the moles of this one, so we can now get the moles of aluminium. Some of you might be saying, Kev, why can't we just use Why can't we just use the 0.5 grams and work out the moles? Ah, good question. That is the total amount of aluminium that we were given. So if you had to go work out that into moles, you would then be saying that we are going to use all of this. But we're not going to have used all of that by the time we reach 5 minutes. Because at the time of 5 minutes, we can see the reaction has not finished yet. So it wouldn't be correct to go use all of that, because then the reaction would be finished. So that's why we're not even going to look at that right now. So we know that at the 5 minute mark, this is information we can use. And yeah, so we're not going to look at that part there. So now we know the moles of hydrogen gas that we have used or formed in the first 5 minutes. It's this value over here. So we can now use the mole ratios with that to see how much aluminium we must have used in the first 5 minutes. So we know that aluminium to hydrogen is in a 2:3 ratio. So if we know that the hydrogen is 6.7347 times 10 to the minus 3, and then we can call this x. You can just do cross multiplication now, and so you're going to end up with 2 multiplied by 6.7347 times 10 to the minus 3, and then 3x. And then to get x by itself, you're just going to divide the left side by 3. And we should end up getting 4.4898 times 10 to the minus 3. Okay, so the moles of hydrogen used at 5 minutes. Now we know the moles of aluminium that we have used up until the 5 minute mark. Okay, so what we could then do is we could convert that into a mass. So let's go use the formula N equals to M over big M. And we know the moles is 4.4898 times 10 to the minus 3. The mass, we don't know what that is. And now the molar mass of aluminium on your periodic table is 27. So then what we do to get the mass alone, we're just going to go and multiply these two values together, and we end up with a mass of 0.12 grams. Now that's not the answer. That is how many grams of aluminium we have used up until the 5 minute mark. So how much aluminium do we have present in the container? So how much has not been used is what they're actually asking. Well, we originally were given 0.5. We've used 0.12, and so we should have, let's write it over here, we should have 0.38 grams remaining. So that is the amount of aluminium that has not yet been used. Now, obviously, rounding off, we all do it a little bit differently sometimes. So on the memo, they allow anywhere between 0.365 up to 0.42. You can get anything between that. Okay, so moving on to 5.1.3, it says, use the collision theory to explain the change in the reaction rate from t equals to 0 to t equals to 5. Okay, so remember in the beginning, they told us that, they gave us a 0.5 gram aluminium strip. So what we have in this experiment is, we can imagine we have some type of container with an aluminium strip. Either it's going to be like floating around, or it's going to be hanging by a string, or it's going to be laying flat on the surface here, or on the bottom here. And then we've got an HCl solution. Okay, so HCl solution, all these little HCl molecules are floating around. And then you've got your aluminium strip. Okay, so the aluminium is not broken up into like a powder or anything like that. It's just a strip. And so we know that as the blue HCl molecules collide with the aluminium, there will be a reaction that takes place. So they say use the collision theory to explain why there is a change in the reaction rate. Now, we know that as a reaction goes on, it gets slower and slower and slower. And that is because as the reaction goes on, what will happen to the amount of this and what would happen to the amount of HCl? Well, your amount of HCl is going to become less as the reaction continues, and your aluminium strip is slowly but surely going to start becoming smaller, and you're going to have less aluminium. And so over time, what would happen is that because you've got less HCl and less aluminium in the container, there's going to be less collisions taking place compared with at the very beginning of the reaction. And so your reaction rate will begin to slow down. But they don't want us to explain this question from the perspective of the HCl, because over here they said, assume that the concentration of HCl remains constant. So they said assume that the amount of HCl doesn't change, which obviously it does, but they want us more to focus in on what's actually happening with the aluminium. So we can just say, as the reaction progresses, the aluminium strip will decrease in size, then say less aluminium particles will be exposed, and then say less effective collisions per unit time, and then lastly reaction rate will decrease. If any of you looked at the graph and looked at the gradient from 0 to 5 and you thought, hey, but this looks pretty constant, I don't really see it becoming less, then I agree with you. They could have done this graph a little bit better. It should have been more of like a curve from the beginning, so like that. Because this makes it almost look, I don't know, I can't really use a ruler, but if you had to put your ruler on this paper, I would imagine that it almost remains straight. Maybe it starts slowing down a little bit over there. It definitely slows down over here. But the gradient seems pretty constant for the first part. So yeah, if you looked at that and you thought, hey, isn't the reaction rate staying constant? It is almost staying constant. But we know from our theory that the reaction rate has to slow down, because as the reaction starts, there's going to be some effective collisions taking place, which is going to then decrease the amount of HCl and decrease the amount of aluminium. And so it then begins to immediately slow down because now there's less particles available to react. Okay, so moving on now to experiment 2. Experiment 1 is repeated, but they now use 2 mole per decimeter cube of HCl. How much did they use in the first one? Experiment 1. Oh, okay, so in experiment 1, they used 1 mole per decimeter. Okay, so just remember that in experiment 1, we used 1 mole per decimeter. Okay, so now we're going to use 2 mole per decimeter, so it's more concentrated for the HCl. Redraw the above graph in your answer book and label the curve A. On the same set of axes, draw the curve that will be obtained. Okay, so this is curve A, they're saying. Then redraw the curve that will be obtained for experiment 2 and label that as curve B. Okay, so if you have a more concentrated HCl, that means you've got more of these particles. Okay, so there will therefore be more collisions taking place per unit time, so the reaction rate will go faster. So instead of your graph going like there, it'll actually go more like there. But the height that we are going to reach is going to be exactly the same. That is because we must remember that the hydrochloric acid is the excess. So by adding more HCl, you're not going to be able to produce more product. Your product at the end is still going to be the same because that is limited by how much aluminium we have, because the aluminium is the limiting reagent. So you must understand that the aluminium is limiting. What limiting means is that the reaction stops when that one is finished. Think about it. When this aluminium strip is dissolved, then what are these awkward people going to do? Like, oh, shit, the party's over. All right, guys, well, see ya, bye. They can't react with each other. So once the aluminium is complete or finished, the reaction is over. You can add as much HCl inside here as you want. You can change the concentration to 3 mole per decimeter cube if you want. Nothing's going to happen because the reaction is finished when the aluminium is finished. So we're not going to make this graph go higher up. We're not going to be able to produce more hydrogen gas just because we added more HCl. All that happens is the reaction is just going to go a lot faster and we're going to get to the end a lot sooner. Okay, and then this last question says that experiment 1 is now going to be repeated using 0.5 grams of a powdered aluminium instead of a 0.5 grams of an aluminium strip. How will the volume of hydrogen gas be produced? Compare. It is not going to change. If you said greater than, you are thinking about something different. You are thinking about the reaction rate, which is the speed. Let me explain. If you have a container that has an aluminium strip, like we had in experiment 1, and you've got some HCl, okay? Then in experiment 3, all we do is we turn the strip or the aluminium into a powder. So let's say we've got that. And then we've got our original HCl. It's the same amount of aluminium in both scenarios. 0.5 grams, 0.5 grams. All that will happen now is that when you've got it like this, where you've got it in a powder form, the reaction can happen a lot faster because this little HCl can react directly with that particle, this one can react with that particle, and this one can react with that particle. Whereas when you have it in a solid strip, it's not easy to access all of the aluminium. You can only access the aluminium that is on the outside, and then only later on, once the outside has been reacted, then you can start reacting with the particles that are in the middle, okay? But by having it in a powder form, you expose every single particle so the reaction can happen a lot faster. But you're not going to produce more hydrogen gas. You're not going to make more product. You're just going to make it go a lot faster. So once again, your graph would just do that. But they're not asking us for the graph. They're saying, how would the volume of hydrogen compare? Well, it's not going to be lower. It's not going to be higher. It's going to be exactly the same. So we're just going to say equal to. Curve X is the Maxwell distribution curve for a reaction under a set of reaction conditions. A change is then made, and they obtain curve Y. What change was made to obtain curve Y? Okay, so we've gone over this before as to the different changes you can do to a Maxwell curve. One of them is a temperature change. The other is a concentration change. And the other is a catalyst. So let's say we have a Maxwell-Boltzmann curve that looks like this. If you increase the temperature, then the graph, or let's start with concentration. If you increase the concentration, the graph just goes higher like that. Okay, that's if you increase concentration. If you decrease concentration, the graph will just go lower like that. So that's if you lower the concentration. If you increase the temperature, the graph moves to the right, and it actually moves a little bit down for some weird reason. So it goes something like that. So that would be an increase in temperature. And then if you decrease the temperature, the graph would go a little bit up and left. So it would go something like that. It's if you decrease temperature. And then if you do a catalyst, that doesn't actually move the graph at all. What a catalyst does is, we must understand that on these graphs, they have an activation energy. So let's say the activation energy for all of them is there. That is your energy of activation. Now, if you decide to add a catalyst, all that happens is that the activation energy becomes lower. So your activation energy now goes there. That is your activation energy with a catalyst. So if we know that curve X is the original curve, and then we've got a curve Y, we can see that it's dropped a little bit and moved to the right, then that is going to be the same as this increased temperature graph over here. So we can just say what change was made. We can say temperature was increased. And then for this question, they say give a reason. You can literally just say peak has shifted to the right. And if you want to know like the reasoning behind all of this, obviously I have made a video on Maxwell-Boltzmann curves. You can just go double check. The reaction of carbon monoxide with oxygen gas is investigated. The reaction reaches equilibrium in a closed container at a constant temperature T according to the balanced equation. Okay. Changes to the conditions of equilibrium are made at different times. The graph shows the results. X, Y, Z represent the gases in the above reaction. First question, what is, or define the term chemical equilibrium? So we know that when this reaction first begins, it only goes in the forward direction. But then eventually, as you start producing CO2, some of that then starts breaking down and going backwards to become CO and oxygen again. And eventually, the rate at which the forward and the reverse reactions take place will be exactly the same. So here's the definition. You don't have to add the dynamic equilibrium. They're looking for the underlined words. It's when the rate of the forward reaction equals the rate of the reverse reaction. At T1, oxygen was added to the container. Write down the letter that therefore would represent oxygen. So you can see that at T1, only this one gets increased immediately like that. So that must be oxygen. So oxygen will be X. At T2, so over here, the pressure is adjusted by changing the volume of the container. Okay, so I want us to quickly imagine a scenario. Let's say you and your grade, okay? Let's say you and your class. Let's say there's 30 people in your class, including you. So there's 30 of you in total. And in one situation, they tell you that you are going to write your exam in your normal classroom, okay? And then in another scenario, they tell you that you are going to write your exam in the hall, but there's only 30 people, okay? And they tell you that you must try sit as far away from everyone as possible. So in the classroom, you might get like, people might be spread out like that. I'm not going to go do all 30 people, but you get what I'm trying to do, right? Then if you have to go put those same 30 people in the hall, can we agree that they would be a lot more spread out from each other? The distance between people will be a lot more than if we were inside a classroom. So that is how I want you to think about concentration. This would be considered high concentration. And then this is a situation where we've got a low concentration. Concentration just means that if you take a certain certain area, you see how many molecules there are. So if you take that same size grid over here, notice you're going to get a lot more people. So concentration just tells you like how many things are there in a given volume. Okay. So have a look at T2. What happened to all of the concentrations? They all became less. Can you see they all dropped? So does that mean that they made the volume smaller, or sorry, they're talking about pressure, but don't worry, let's first talk about volume. How do you make the concentration become lower? Do you make the volume larger or smaller? Well, think about this. Notice that when you make the volume larger, then what did we do to the concentration? We made it less. So a larger or an increase in volume will decrease concentration. And we can see that's what happened over here. So we've definitely decreased the volume. Now, how does that affect pressure? Well, you can still think about this. Imagine that you and your classmates, your teacher says you can stand up and you can start walking around, but you have blindfolds on, okay? So in which scenario do you think you guys are going to walk into the wall more often? Are you going to walk into the wall more often in this scenario or in this scenario? Well, definitely in this scenario, because there's less volume to move around. So the chances that you're going to bump into the wall is going to be a lot more. So the smaller the volume of a container, the higher the pressure. Remember, pressure is due to the gases bumping against the container walls. And so when you increase the volume, or when you decrease volume, you increase pressure, and when you increase volume, you decrease pressure. Okay, so volume and pressure are inversely proportional. If you make volume small, pressure goes up. If you make volume large, pressure goes down. So we just said that over here, we increased the volume. So what does that do to the pressure? Pressure will go down. So at T2, the pressure is adjusted. So was the pressure increased or decreased? The pressure was decreased. And what was the reason? So for 6.1.4, what was the reason that allowed us to see that? Well, we just saw on the graph that all of the concentrations decreased. So we can just say all concentrations decrease. Okay, this is question 6.1.5. Write down the name or formula of the gas that is represented by letter Z. So we know that X is oxygen. And we can see here that oxygen and CO, carbon monoxide, they are both reactants. So they will have the same shape on the graph. So you can see that over here, oxygen goes down, and this one also goes down. Then over here, we can see oxygen goes up, and this one goes up. Then we can see oxygen goes down, and the carbon monoxide, or that one also goes down. So this graph over here is following the same pattern as this one. Okay, obviously it won't be the same at that part because that's where we increased oxygen, but you can see that the response is always the same in both graphs. So this here is going to be carbon monoxide, so then this one must be CO2. So it says, write down the name or formula of the gas that is represented by letter Z. It would be carbon monoxide. And what's the reason? You can literally just say that Z follows the same trend or pattern as X. Okay, and then we've done that one. Okay, so this one says, what change in temperature is made at T3? Choose from increase or decrease. Okay, so let's just first, without even looking at this reaction, let's just try to figure out which reaction is favored. So we can see that the CO2 goes up after T3, whereas X and Z, they go down. Okay, so the amount of CO2 is going up and the amount of oxygen and CO is going down. So definitely the forward reaction is favored. okay? So that's the first important little thing we've noticed. Forward reaction is favored. So can you see that the forward reaction is exothermic? Remember, that means exothermic. So we can say that forward reaction is exothermic. So therefore, forward reaction is exothermic. Why do I say that? We'll check. The forward reaction is favored. We saw that from the graph. The forward reaction is exothermic. We saw that from the reaction. So what is the overall conclusion? The forward reaction is exothermic. So you need to understand, why would the system... So you got to try to think about, what did they do at T3 so that the system responded like this? Something was done at T3. They either increased or they decreased the temperature. What do you think they did? Well, we know that when the exothermic reaction is being favored, the system is busy heating up. So why would the system do that? What do you think they did at T3? Well, at T3, they would have made the system, they would have decreased the temperature. So they decrease the temperature at T3. The system doesn't like that, so that is why it then goes on and it reacts like this, and it favors the exothermic so that it can raise the temperature again. So therefore, temperature at T3 was decreased. So the temperature at T3 was decreased, which might make you think of endothermic, which is fine. But then remember, the system says, hey, I don't like what you're doing to me. Why are you making my temperature lower? I'm going to change that, and I'm going to reverse that, and I'm going to make the temperature higher again. And that is why it then goes on and it does this, and it favors the exothermic reaction so that it can try heat itself up again. Okay, so we've kind of done 6.1.7 and 6.1.8 in one go. So in an exam, you would have just said decreased over here. And then for your explanation, you could have just put that over there. Carbon monoxide gas reacts with water vapor, and check that, 9 marks. Reacts with water vapor at T degrees. The reaction reaches equilibrium according to the following balanced equation. Okay, so initially we have that many moles of CO, that many moles of H2O, that many moles of carbon dioxide, and that many moles of hydrogen gas. And if the equilibrium constant for this reaction is 4, calculate the mass of carbon monoxide present at equilibrium. Okay, so it's definitely a KC table kind of question. Let's go draw it out. Okay, so at the beginning, I'd just like to fill in the reaction. So that's just going to be carbon monoxide plus H2O, giving us CO2 plus hydrogen gas. Right, and they said it's balanced, and then we're going to put the initial number of moles. So this one, we start off with 0.6 over here, 0.6. Now, normally, if they don't mention anything, we would normally put zeros over here, but they've actually given us some starting material. So that's perfectly fine. There's nothing wrong with that. So it's going to be 0.1 and 0.1. Then we look at the change, which they don't really tell us anything at the moment. Okay, so we won't fill in anything there for now. Then we've got mole at equilibrium. I'm just going to write it like that. And then we've got concentration at equilibrium. Okay, so what else do we have? Okay, we know what the equilibrium constant is, but they don't tell us anything about the change or anything like that. All right, that's fine. So we can just make the change. This one we know is going to go down, so we'll just make it go down by x. Now, can you see that the mole ratio is 1 to 1? So this would also go down by x. And then all of them are 1 to 1, so these would go up by x. For every 1 mole that goes down, this one would go down by 1. For every 1 mole that this one goes down, this would go up by 1, and this would also go up by 1 because their mole ratios are all 1 to 1. Remember that with this change row, you always base it on the mole ratios. Okay, so there we've just got that. Now for your moles at equilibrium, you just add these columns together. So that's going to be 0.6 minus x, 0.6 minus x, 0.1 plus x, 0.1 plus x. And then to work out your concentration, you just use C equals to N over V. What is the container volume? 2 decimeters. So you're just going to say 0.6 minus x over 2, 0.6 minus x over 2, 0.1 plus x over 2, and 0.1 plus x over 2. Very straightforward. Now we can just go do Kc. So we know that Kc is your concentrations of all of your products over your concentrations of your reactants, all at equilibrium. So that's going to give us the concentration of hydrogen gas multiplied by the concentration of CO2 gas divided by the concentration of carbon monoxide multiplied by the concentration of H2O. And so we know that the Kc value is 4. So we're going to say 4 equals. Now your hydrogen gas is that. So 0.1 plus x over 2. Your carbon dioxide, is the same. Then we're going to say 0.6 minus x over 2 and 0.6 minus x over 2. There's no exponents, like there's not a 3 there, for example, or a 2 over there, because the exponents are always going to be these numbers in the front, and they are all 1s in this scenario. Okay, and now it just becomes something that you need to solve. The first thing I want us to just realize, you might have gotten there by a slightly longer way, but let me just speed it up for us. Eventually, when you multiply these two brackets together, you're going to get 2 times 2 at the bottom, which is going to be a 4, okay? And then you're going to do the exact same over here, and you're going to get a 4. Those 4s are eventually going to cancel top and bottom. So I'm just going to cancel them out immediately. So what we actually just have now at the top is this, and this. And then at the bottom, we're just going to have that, and that, okay? Now, to make the maths very, very easy, check this out. These two together, they can just be 0.1 plus x to the power of 2. And these can just be 0.6 minus x to the power of 2. What we can then do is just cross multiply. So this is going to end up going there to the 4. And so you're going to end up with 4 times by 0.6 minus x to the power of 2. And then on this side, we're going to end up with that over there. I'm then now I'm really making this nice and short, but if you don't want to and you want to go multiply everything out, you can. It's perfectly fine. But I'm just going to square root both sides, because I know that the square root of 4 becomes 2. I know that the square root of that just gets rid of the square, and so you're just left with 0.6 minus x. And then on this side, it just gets rid of the square, so you just end up with that. Suddenly, things are looking quite straightforward. Like I said, though, if you were a student over here and you wanted to just go multiply everything out and you don't feel comfortable with the steps that I've used, remember, I've been doing this kind of maths for many years. And so for me, it comes fairly straightforward. Whereas when I was a student, I don't know if I would have wanted to do it that way. I would have felt a bit uncomfortable because it might have felt a bit outside of my comfort zone. And so I maybe would have done the longer method where I multiplied out, but at least I feel safe doing it that way. And so you can do it like that if you want. Okay, now in terms of actually going ahead and solving, I'm going to multiply the 2 into that bracket. So it's going to become 1.2 minus 2x equals to 0.1 plus x. And then I'm going to eventually end up with 3x on the right and then 1.1 on the left when you take this over and you take that over. And then if you get x alone, you'd say 1.1 divided by 3. you get 0.37 if you round to 2 decimals. Now, that's not the answer. That is just your X value. So the question says, calculate the mass of CO at equilibrium. So let's go to this column or this row, and let's go to the CO at equilibrium, which is 0.6 minus X. And so we can then go work out the moles of CO at equilibrium by just filling in the value of X. And so the moles of CO at equilibrium, we know was 0.6 minus X. So that's therefore going to be 0.6 minus 0.37, which is 0.23. Now we can just use the normal mole formula, and we can say 0.23 equals to mass. The molar mass of carbon monoxide, well, carbon on the periodic table is 12, oxygen is 16, so together that would be 28. Then to get the mass alone, you're just going to say 0.23 multiplied by 28, and that'll give us 6.44 grams. Due to rounding off and all of that, on the memo, they allow you to get anywhere between 6.44 and 6.72 grams. Hydrated potassium carbonate, okay, so it's a potassium carbonate with water attached, is a weak base. Okay, don't worry if you haven't seen this before. It's okay, I haven't really either, or at least not in questions like this or in any of the theory. So it's not like you needed to know that that's a weak base. That's why they're telling you. A solution is prepared by dissolving some of the solid in water. First question, define the term weak base. Okay, so typically when we look at acids, we know that acids like to ionize, okay, and bases typically like to dissociate. We have got some exceptions like NH3, which is a base that ionizes. Now, if something is strong, then it will ionize. Or if something is a strong acid, let's say, then it would ionize completely. And if it's a strong base, it would dissociate completely. Now, if it's a weak acid, then it ionizes partially. That means not really, just a little bit. And then if it's a weak base, it'll dissociate partially. Okay, now we also know that when acids ionize, when it ionizes in water, we typically produce, so let's just say here, when acids ionize in water, we produce, or let's rather say they produce. I know it's the 21st century and we can identify as chemical molecules if we want to, but let's just try to keep things a bit normal. So when acids ionize, I am a chemical molecule. Thank you very much. When acids ionize in water, they produce H3O, hydronium ions. And then when bases dissociate in water, they produce hydroxide ions, so OH minuses. Okay. When acids ionize, if it's a strong acid, it ionizes completely, so it will produce a lot of H3O+. If something is weak, then it won't produce a lot. So for example, if you have a weak base, then it would dissociate in water, but it would only dissociate partially, like we said over here, and so it wouldn't produce a lot of OH minus. It would only produce a small amount of OH minus. Now the actual definition is this. Okay, so here we go. A weak base dissociates. Now they've allowed you to say ionize as well, and the reason for that would be because you do get this one exception in bases, which is NH3, ammonia, which can ionize. That's why they can't ignore that part, okay? So weak bases, but typically you want to just say that weak bases dissociate. You can either say incompletely or partially, I like to use the word partially, to form a low concentration of OH ions. Okay. Okay, moving on to 7.2. Write down the formula of the conjugate acid of the carbonate ion. Okay, so we know that the only difference between a like a conjugate acid and its base, or a base and or a conjugate base and its acid, if you've watched my videos on conjugates, the only difference between them is the hydrogen ion that gets moved from the one to the other. So if they want to know what is the conjugate acid of this, then that means this thing must be a base. So what we'll do, if this thing is a base, it means that it likes to accept hydrogens. So if you then give a hydrogen to this thing, it then turns into a conjugate acid. So if we add a hydrogen ion, now a hydrogen ion is positive, so we're going to put it in the front over there, but now we can't say 2 minus anymore. What is the original charge was 2 minus, but now you're adding a 1 plus. So what is negative 2 plus 1? Well, that's going to now make the charge negative 1. So you can just put it like that. Okay? And so that is the answer. HCO3 minus. Remember, whenever you're going between conjugates and like conjugate acid and its base, or conjugate base and its acid, like we said, it's just the change of a hydrogen. Now, if you are confused in an exam with what's what, then just remember, what is the only thing that you can do to this? Can you take a hydrogen away? Well, no, because there is no hydrogen over there. So the only thing you could have done to this thing is give it a hydrogen. They could have made the question a little bit more complicated, and they could have given you HCO3 minus over here, and then they could have mentioned the whole conjugate, blah, 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 and then you wouldn't, and then if you don't understand your theory very well, you wouldn't really know whether you should take this away or whether you should add another one. But in this scenario, you got lucky if you didn't understand your theory, because you can't remove a hydrogen here. So the only thing that could happen here is that it gains a hydrogen. Okay. Now, a hydrochloric acid solution, HCl, of concentration 0.1 mole per decimeter is titrated with the prepared carbonate solution of unknown concentration. The balanced equation is this. Okay, so there's no more hydrate in the thing. Okay, cool. The results of the titration are given below. Okay, so they did the experiment twice. They gave us the volume of HCl that was used. We also have the concentration of HCl, which is fantastic. And then they gave us the initial burette reading. Okay, so let's quickly talk about, you've probably done the experiment in class when you had to use a burette. But let's just talk a little bit more about the way that these readings work. Once you understand it, this table is an absolute joke on how easy it actually is. Okay, so a burette, it's this device here. You've maybe done an experiment in class, and then what you would have done is you would have had like another little beaker underneath that, and you would have opened this little tap, which is this one over here, by rotating it like that, and then liquid would begin to fall. And what we got to do is try work out how much liquid did we pour into here. So, you know, when you start the experiment, you fill this up. And what's weird about these burettes is that the 0 is over here, and then right at the bottom here, if it's like a 50 mole, then you would put a 50 over there. Now, you don't have to fill it up to the very top. You could fill it up maybe up to there, for example. Or like, let's rather use this diagram. So maybe you filled it up to the 19. And then you opened up this little tap and you started pouring liquid into here. And you keep pouring, keep pouring, keep pouring. And eventually you stop when this solution changes color, because we have some type of indicator in there. Okay? Let's say when the color change happens, you are now over here. So your liquid has gone all the way from up here, which you can think of over there, and then as you poured the liquid into this flask, this volume became less, so it went down, 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 and maybe it's now here at 22. Okay, so that is what. So then what you could do is you could then say, okay, well, 22 minus 19, well, that would give me 3, and that would then tell you how much volume you have added into this flask. And that is exactly what they're doing here. So this one here is the 19. This one here is the 22. And then this one here is what you get when you subtract them. Okay? So you just got to think about it a little bit differently. If I know that my initial burette reading is 6.5, and then I know that I used a total of 20.05, so that means I added 20.05 into there, then how would you actually work out this value? Well, then you would actually say 6.5 plus 20.05, and that would give you 26.55. So what that would look like is on your burette, you would have started at 6.5, it would have gone down to 26.55, and then if you minus them, it would tell you how much you used, which was this value over here. Okay, so that means that this p-value is going to be 26.55, and then to work out this one, you can just say 48.3 minus 20.15 to work out this value, and that would give us 28.15. So that would look, what that would look like on a burette is you would have started your experiment at 28.15. It would have ended at 48.3, and then you would have minused them to see how much you used, and you would have gotten 20.15. Okay, so we now have the values here. Okay, so let's go fill that in. So for P, we ended up getting 26.55, and that is measured in centimeters cube because of this. And then for Q, we got 28.15, and that's also measured in centimeters cubed. Okay, so we have run 1 and we have run 2. Fantastic. Now it says methyl orange is used as the indicator. Explain why methyl orange is the most suitable indicator for this titration by referring to the pH at the equivalence point. Okay, so it all comes down to this. We get all different types of indicators. We get like bromothymol blue, we get phenolnaphthalene, whatever you call it, and then you get like methyl orange as an example. Okay, guys, so just listen carefully to this explanation. It's going to make a lot of sense. Okay, we actually don't need really going to focus in on these ones right now. The most common ones that they will refer to in grade 12 and 11 is these ones over here. So we need to just understand a few things. They told us that this is a weak base. We should know from theory that this is a strong acid. So remember, we've got this thing in grade 12 with acids and bases called hydrolysis. Okay? And we should know that when you take a strong acid plus a strong base, then at the end of the titration, the pH would typically be 7. If you take a weak, and I've made videos on hydrolysis, so you can go look at that. I'm not going to go into all the details now, but if you take a weak acid and a strong base, at the end of the titration, the strong base would end up, you can just think of it like this, but I do explain it in other videos on hydrolysis, how it works. But the strong base, you can imagine that that's going to be the dominant factor, and so your pH at the end is going to be larger than 7. It's going to be more basic, because you have a strong base with a weak acid, okay? Then if you have a strong acid and a weak base, well, then your pH at the end of the titration would be smaller than 7. Because now you have a strong acid, which is acidic, which has a low pH, which would dominate a weak base. And then if you have a weak acid and a weak base, the factors cancel each other out, and you actually just end up with a pH of 7. So in this experiment, we have a weak base and a strong acid. So a weak base and a strong acid. So that means that at the point when the titration is finished, the pH is actually going to be smaller than 7. So we need an indicator that will have a low pH. That is why we will not use phenolnaphthalene, because that changes over there. We won't use bromothiamyl blue because that, I mean, it might work, but it's really like, it's almost at 7 itself. But methyl orange is perfect because it goes into the very low pHs. And we said that when you have a strong acid and a weak base, because of this hydrolysis thing, which, like I said, I've made videos on it, so you can go watch that and you can understand exactly what's going on behind the scenes. But we will expect that we're going to end up with a pH that is smaller than 7. So it makes sense that we will use an indicator that changes at slightly lower than 7 pHs. Okay, so let's just read this question again. Methyl orange is used. Explain why methyl orange is the most suitable by referring to the pH at the equivalence point. So at the equivalence point, which is the point where the color changes, the pH will be lower than 7. Okay, that's all that you need to say. Now for 5 marks, calculate the concentration of K2CO3 solution. Okay, so in class, when you did this experiment, or maybe you haven't, but just listen to how it works. In an experiment, we often do it more than once. So we do 1, 2, just to get a better accuracy. So what we'll do, we're not interested in any of this. We're interested in these values here. And what we would do in real life is we would use the average of those. Okay, so the average of those two numbers is going to be, if you just add them together and divide by 2, you're going to get 20,1. So that is the volume of K2CO3. So we have the volume of K2CO3. We have the volume of HCl that we used in both experiments. It's the same. And we have the concentration of that. So if you've watched my videos on titration, it's very easy. All you're going to do is use this information to work out the moles, because you've got the volume and the concentration. You then use the mole ratio to work out the moles of this one. And then you've got the moles and the volume here to get the concentration. You don't have to use special titration formulas, you know, like you get ones that are like C1V1 over C2V2, but you can if you want to. But I tell learners, if you don't know what they are and you don't want to use them, you don't have to. But if you do know what they are, then now's the perfect time to use them. I don't use them. I just go use this information here to work out the moles of HCl. So I know that C equals to N over V, but I know that if I rearrange that formula, I can end up with that. And that's going to give me, for HCl, its concentration was 0.1. And its volume in decimeters will be 0.025. And that's going to give 2.5 times 10 to the minus 3 moles. Okay, so I know the moles of HCl. Now I can just use the mole ratio to get the moles of K2CO3. So I know that the mole ratio of K2CO3 to the moles of HCl in the equation is 1 to 2. So if I then fill in 2.5 times 10 to the minus 3, I can see, without having to do any fancy maths now, I can see that the HCl is always going to be double the K2CO3. So I can just divide this number by 2, and we get 1.25 times 10 to the minus 3. So the moles of K2CO3 is going to be 1.25 times 10 to the minus 3. Then I've got the volume of K2CO3, which was the 20,1 centimeter cube. So I can just use C equals to N over V, and the moles is what we got here, so 1.25 times 10 to the minus 3 divided by, now remember this needs to be in decimeters, so if you divide that by 1,000, you get 0.0201. And if we go work this all out, we should get 0.062, and that's going to be measured in, it's a concentration, so it's mole per decimeter minus 3. Okay, and then this last question says that the above K2CO3 solution used in the titration was prepared by completely dissolving that many grams of the hydrated potassium carbonate in 600 centimeter cube of water. Calculate the value of X in the formula. Okay, so quite an interesting question. So there's a number of different ways you could handle this one. One of them is, and I don't really like what they've done, because they started off in the very beginning saying that hydrated potassium carbonate, and then they said over here that titrated with the prepared solution above, but then they didn't keep the XH2O, but it is actually there. Maybe they just didn't want to cause any extra confusion, because it wouldn't have affected any of these calculations that we did. So the point that I want you to understand is that this concentration that we just worked out in 7.5 is the concentration of that hydrate as well. It's the same solution, okay? So we have the concentration of that solution. We also, and now something else that you actually that might confuse a lot of learners is, here we had the volume of K2CO3, but why are they now giving us a new volume? Like, how does this all work now? Well, what happened is the following. Once upon a time, there were some scientists who were working in a laboratory because they wanted to do this experiment. And what they did is they made a big batch, 600 centimeters cubed of this K2CO3 XH2O. They made a batch of 600 centimeters cubed. Then for the actual experiment itself, when they poured it into the burette, they only used that amount over there, okay? And what we've just gone and done in all of these previous questions is we used the average of those two, and what we were able to do is we were able to work out the concentration of that solution, of the solution. But what you need to understand is, where did this solution come from? It originally came from the bigger batch, which is 600 centimeters cubed. But whether you look in the big batch or whether you look in this little part in the burette, the concentration is the same. Think about this being a big 2-liter Coke, and think about this being a little glass that you pour some Coke for yourself at your house. Like you take the Coke out the fridge and you pour some for yourself into a glass. The Coke is going to taste exactly the same, right? Because the concentration or the sweetness doesn't change. We're not adding in more water or taking water out. So what I'm trying to say is that the concentration that we calculated in 7.5 is also the concentration that we can use for this 600 centimeter cube. So we can then go use the formula C equals to N over V, and we can now go work out, if we have the concentration from the previous question, what did we say? We got 0.062 in the previous question. We can then go use that volume of 0.6, and what we could then do is work out how many moles of this hydrate do we have? How many moles of the hydrate do we have? And so if you're to get the moles alone, if you're feeling a little confused with this question, it is very weird. I don't like it too much, but you might have to just watch this a few times and you'll get it. Okay, so now we have the moles of the K2CO3 hydrate, which was originally from this big 600 centimeters. It's not the moles that we got here, because when we were doing this little experiment, we were only using a smaller volume, but we are now using the larger volume because that's what they are, that's what they're referring to now. Okay, so that is the moles of the hydrate that we have. Now we could use this formula And we've got the mass that they gave us. And we also have the moles, which we've just worked out. And we could go work out the mass on the periodic table. Or we could calculate that, and then we can go, and that'll easily allow us to work out what the value of x needs to be. So we can now say 0.0372 equals to the mass that they gave us. You remember that this mass that they gave us is the mass that goes with this volume of water, not this volume over here. And that is why we had to do this little conversion that I've just done. Okay. And the reason why we couldn't use the moles that we had in this one. The only thing that stays constant between the 600 centimeter cube and the 20.1 is the concentration. Just like I said, if you have a large Coke and you pour some into a glass, the concentration or the sweetness stays the same. And then the molar mass on the periodic table is what we're now going to actually calculate. So if we now go and calculate capital M, you're going to get 6.525 divided by 0.0372, and that'll give you 175.4 grams. Okay. So now, if we go look on the periodic table at K2CO3XH2O, you would see that the mass of this is, well, it's 80, because it's 40 and 40. So that's going to be 80 plus 12 plus 48, because there's 3 oxygens, and then plus X waters. We don't know how many waters we're going to have, but each of these waters is going to be 18, the mass, because hydrogen is 2, because there's 2 of them, and then 1 oxygen, which is 16. So that's the mass of water, and we know that all of that should give us 175.4. 175.4. And then you're just going to solve for x. And if you do this correctly, you should get 1.97. But then remember that x, when it's in a formula here, has to be a whole number. So because this is very close to the number 2, you round it up to 2, and so x is 2. Dilute hydrochloric acid reacts with magnesium according to the following equation. Use oxidation numbers for each of the reactants and explain why the reaction is a redox reaction. Okay, so this is quite interesting. So we know that when you have a element that is completely by itself, it has an oxidation number of 0. Then we know that with HCl, H is going to be positive 1, Cl is going to be negative 1. With this one here, Cl is going to be negative 1. And this one here is a pure element by itself, so that's 0. And then to work out magnesium, you can just look on your formula sheet, and it's in column 2, so it's just going to be positive 2. Okay, so why is this a redox reaction? A redox reaction is when oxidation numbers change. So what we can see is that magnesium goes from 0 to positive 2, and hydrogen goes from positive 1 to 0. So we can just say, to answer this question, explain why this is a redox reaction, we can say that magnesium goes from 0 to positive 2, and hydrogen goes from, what did it go from? From positive 1 to 0. Okay, now this question says, write down the formula of the oxidizing agent. So oxidizing agent is not the substance that is oxidized. This confuses learners all the time. The oxidizing agent is the substance that is reduced. Okay, and reduced is when your oxidation number decreases. So whose oxidation number decreased? Well, you see how this one went from positive 1 to 0. So it's that one that decreased. So your oxidizing agent then came from this one over here. So you will say HCl. Even though it's not the Cl, it's just the H, you always write the oxidizing or reducing agent as the whole formula that it's a part of. If you do, however, only want to mention the H, then you must just do it correctly. You must say H plus, because that's what it currently is in that form. It's got a +1 over there. So you just say H plus. Okay, now this question says that, first over here. It is observed that dilute hydrochloric acid does not react with copper at 25 degrees. Explain this observation by referring to the relative strengths. Okay, so we're going to go get our table. I like to use table 4b. And all you're going to do for now is you're just going to go circle things. So we got hydrochloric acid. So that's HCl. And we've got copper. Now, HCl has a charge of +1, Cl has a charge of -1, or an oxidation number, and then Cu is 0. So you're going to go find all of those. Okay, so we have the H+, there it is. We have Cl-, which is down here at the bottom, and then we have copper. Now, the reaction with copper is usually the one with the 2+ and the 2 electrons, so we're going to take that one there. Okay, now obviously I'm using table 4b. On table 4a, the principle stays the same, but you're going to just have to look at your arrows. So the way it works is the following. If you look at the arrow on the left, it's going downwards, okay? And if you look at the arrow on the right, it's going upwards. So there, the only time that a reaction can happen spontaneously, which means it can happen by itself, is when the thing that is on the right is above the thing that is on the left. So for example, showing in green, if you had a situation like this where the thing on the right is higher up than the thing that you've highlighted on the left, see what I've done there? Then a reaction will happen. Or if you have something like this on the right is higher up than this one on the left, then a reaction will happen because I'm following the arrows. But we don't have that over here. There is nothing on the right that is higher up than anything on the left. The thing on the left is right here at the top. These are both below it. So a reaction will not take place. Now, when you give your reason, they've asked us to use reducing agents. So we're going to use the reducing agents over here. Now, you're not going to use, you're going to have to mention something about this one on the left, but you're not going to use the Cl- because the Cl- is already together with the hydrogen. If a reaction did take place, it would be because this one is able to do something to this molecule. It wouldn't be because this thing is doing something to that, because these two are already together. So we can ignore that part. So what we're rather going to look at is this one, and it's over here. And all we're going to say is copper is not a strong enough. Now look here, copper's on the right, so we call it a reducing agent. So it's not a strong enough reducing agent to reduce H+ to hydrogen. So let me explain that. This copper is not strong enough to cause this thing over here to become hydrogen. So it's not strong enough to cause this thing to change from what it already is. And that's it. That's how they want you to explain it. Okay. Now, new question. Will dilute nitric acid be able to react with copper? Okay, so now we go find everything on the table again. So nitric acid is broken up as H. Let's write it out. HNO3 plus copper. So the H is +1. NO3 is a polyatomic, which has a charge of -1. We can see it over there. And we can also see it over there. And copper, we already know. Okay, so we've got the hydrogen up there. NO3, not really 100% sure which one we would use, but don't worry, let's just circle both of those for now. And then copper. Okay. So now they want us to explain it in terms of the relative strengths of the oxidizing agents. Okay, now we have said that a reaction will happen if the thing on the right is higher up than anything on the left, because these ones on the left must be lower down. So can you see that we do have a scenario happening? Whether we choose this one or this one, can you see that the copper on the right is higher up than these that are on the left? So will a reaction be able to take place this time around? Yes, because now we have a situation where the thing on the left is lower down than the thing on the right. So they want you to explain it in terms of oxidizing agents. So you could say, we can say yes, and then we can say NO3 minus is a strong enough. Then you can say oxidizing agent and will be able to oxidize. That's why it's an oxidizing agent. It'll be able to oxidize the copper to become copper 2+. So this NO3 or this one, doesn't matter, will be strong enough to be able to cause this copper to oxidize and become Cu2+. A galvanic cell is represented by the following cell notation. Write down the balanced net ionic equation for this cell. Okay, so we know that the left-hand side is always your anode, and your right-hand side is always your cathode. So cathode is always where you have reduction, and anode is always where you have oxidation. Okay, let's go get our tables. So if we go find the PB reaction, PB is over there, and the Fe3 to Fe2 is over there. Okay. Now we know that this reaction is your anode, which is oxidation. So remember, oxidation is when you write it from right to left. So that's your first reaction, Pb becoming Pb2 plus 2 electrons. And then your Fe reaction is your cathode, when which is when it's written from left to right. So that's going to be Fe3 plus an electron gives you Fe2+. Now, in order to get the net equation, these electrons have to be the same so that they can cancel out, because we're going to put these together now. So what we will do is we will multiply this whole reaction by 2. So that means there will be a 2 there, a 2 there, and a 2 there. Now we can put the two reactions together. So Pb plus 2Fe3 plus 2 electrons. So you see I've added everything on the left of the arrows. Okay? Now we're going to put the arrow, and we're going to put everything on the right of the arrows, which is that part and that part. So it's going to be Pb2 plus 2 electrons plus 2Fe2+. So you see how the electrons can cancel now? That's exactly what we want. And so that over there is the reaction. You don't have to put the phases like the aqueous, the solid. You can. They won't mark you wrong, but you don't have to. Okay, and then we could actually just make this a little bit more simple, like neater, like that. Okay, and now they say a stronger reducing agent is now used with the same oxidizing agent under the same conditions. Okay, so we know that this reaction went that way, and this reaction went that way. So this, we started with this one up here, so that is a reducing agent, as we can see. And then this one down here is your oxidizing agent. Okay, so that is your oxidizing agent. And then this here was our reducing agent. What they then said is that a stronger reducing agent is used. So it would be something that is even higher up on the table on the right-hand side, if we are using table 4b, of course. So it says, how will this affect the initial EMF? Well, as you go, or let's quickly remember that to calculate the cell, we always take the cathode minus your anode. Okay, now we know that the cathode is where reduction happens, so that was this one. So that's a 0.77, so we say 0.77 minus. Now the current anode value was negative 0.13, okay, so that ends up becoming a plus, right? Now if we go even higher up, these values become even more negative. So let's say we even just went up to that one. Then you would be putting a 0.14 over here. So you would be plussing, and it would be a larger value. And so your EMF value would increase. So we'll just say increase. And they didn't ask us to give a reason. Because once again, as you go further and further up, these values are going to become more and more and more and more and more negative. You can even go look at your table 4b. They're going to become very negative. And so that very negative next to this negative turns it into a positive, and so you end up making this value much larger. This will be a really nice, easy question. It's just going to be a quick little calculation. So all we'll do, they tell us that a strip of silver, okay, so that's a strip of pure silver, is added to a 1 mole per decimeter solution of PbNO3, okay? So that means we're going to have some Pb ions flowing around over here. That is what we have been given at the start. Okay. And they pretty much, this NO3 is just a spectator ion. It doesn't get involved. So they pretty much want to know, will a reaction happen? And you can use a calculation to show it. So we're going to go get our table. I like to always use table 4b. And all we are going to go do is just go find out what we have. So the Ag is over there. And the Pb2 plus is over there. Now, if you know your tables very well, immediately you'll see that a reaction is not going to happen. But let's pretend, so what we'll do, because they want us to see a calculation, let's pretend a reaction does happen, and then we'll show that it can't. So if a reaction does happen, then we can see that the Ag will go to become Ag plus, so it will go in that direction. And this will turn into Pb, like we can see over there. So if you look at the direction of here, that is oxidation. And if you look at this one, you should know that that is reduction. Now we know that if you calculate the voltage value, it's always your cathode minus your anode. Now we know that cathode is always where reduction happens, and anode is always where oxidation happens. And so if we had to work out the E cell, it would be the where the reduction is happening, which is negative 0.13, minus where your oxidation is happening, which is 0.8, and you would get negative 0.93 volts. So because this value is negative, it means that the reaction is non-spontaneous, meaning that it cannot happen naturally by itself. If you got a positive answer, then the reaction is spontaneous. The simplified diagram below represents an electrolytic cell. The electrodes are made of carbon. Define an electrolyte. An electrolyte is a solution that can conduct electricity. That's literally it. It's a solution that can conduct electricity. And then I see they also want you to say, due to the movement of ions. Okay, let me get the other definitions that you could also use. Okay, there we go. So it's, you can choose any one of those. All right. Okay, next one. Write down the predominant. Why are you using words like that? Just say write down the oxidation that takes place in the cell. Okay, right, let's see what we have here. So we've got concentrated NaCl. So this is going to be, it's going to be broken up into Na plus and Cl minus. Now, all that will happen is that, you know, the Na plus is naturally going to be attracted to this electrode because it's negative. And then the Cl minus would naturally be attracted to this electrode because it is positive and opposites attract. Oh, I guess I see why they're saying predominant, because this is that section now in electrolytic where you've got an aqueous solution, which means what? There's also going to be water in the container. And that water can react under certain situations. So I've made videos on this, guys, where we've got an aqueous solution in an electrolytic cell, and I've explained how water can win, when it can win. I've also explained when they use the word concentrated and how that affects the answer. So let's go get our table quickly. I'm going to go get table 4b. Okay, so if you haven't watched my video on this, please go watch it. It makes it very easy. I'm not going to go into all the details now. Electrolysis of an aqueous solution. And at the end of the video, I specifically mention what you should do when they have concentrated and blah, 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 blah. So what we have in this situation is we have Na+, so we circle Na+. We've got water. So the two waters that we use in grade 12 is this one over here, and then this one over here at 1.23. Okay, obviously there's a whole bunch of other waters, but those are the ones we look at. Then we've also got Cl-, which is over here. Okay, now these two are going to compete with each other because they are both on the left of the table, and these two are going to compete with each other because they are both on the right. Now, to work out who wins, you just look at the arrow. So we can see that the lower down the arrow, the stronger the substance becomes. So we can see that the H2O is lower down than the Na+, so it is the winner. It will react. Okay? And they said, which is the predominant oxidation? Okay, so that's not going to be for that one because these reactions are both reduction reactions. So it's these two that they're asking us to compete. Okay, so we know that that's oxidation and that's oxidation. So now listen carefully. Normally you would use the arrows and you would see that H2O would be the winner because it's higher up, because this arrow is going upwards. However, I've explained in that video where I talk about electrolysis of aqueous solutions that under certain situations we can override the water and we can actually cause the Cl- to react. And that is when we use a concentrated solution. So the Cl- in a concentrated solution will actually beat the water. So the oxidation reaction is actually going to be this one. And so you're just going to say 2Cl- goes to Cl2 plus 2 electrons. Some of you might be saying, Kevin, does that mean that the winner over here is actually going to be the Na+? Nope. If you go watch that video of mine, the only thing we need to keep in mind is that Cl has this ability to win. Don't worry about any other scenarios. It's only when you have a concentrated solution that the Cl specifically has the ability to beat the water. Okay. Now it says, write down the names of the products that are formed at electrode Q. So electrode Q is where the Na plus and the water are going to compete. So who's going to win over here? We said that the winner is going to be the water. So what are the products going to be? The products are going to be hydrogen gas and OH minus. Don't say Na because that's not going to react. Okay, and then it says explain the answer to question 9.2.3 by referring to the relative strengths of the oxidizing agents involved. So we can just see here that H2O is a stronger reducing, see how it's, is a stronger oxidizing agent. Because you can see here, look at the arrow, as it goes down, it says increasing strength of oxidizing agent. So the lower down it goes, the stronger it becomes as an oxidizing agent. So because H2O is lower down than the Na+, the H2O is a stronger oxidizing agent than the Na+. And then we can just say, therefore, H2O will be reduced. So yes, it's a strong oxidizing agent, but that doesn't mean it's oxidized. That just means that it oxidizes other substances. So H2O is a stronger oxidizing agent than the Na+. Therefore, the H2O will rather be reduced and go like that.